Right. So good morning, everyone. I'm going to start today's proceedings. We've got seats there, ma'am, if you can make your way to that corner. So my name is Ahmed. I'm part of the organizing team here at Zak. Quickly introduce the Zak World of Façades conference series to those who don't know. This is our second time around in Washington, D.C. We were here back in June 2023. Lots has happened from there until now. So these are the events which we are basically doing in 2026. If you see, they're spread all across the globe. We've organized this event in 48 countries as on date. I think by end of this year, we should hit 51 countries. We're going to a lot of new countries this year, again, where there has never ever been a facade-specific conference. We're going to Albania. We're going to go to... what's new? We've gone to Rome, which is new for us in Italy. We've been in Milan earlier. We did Barcelona last week. We were in Madrid earlier. Netherlands is a new country on our radar. Cyprus, we did Greece last year. That was good. So we keep organizing these events in different parts of the world. I think there are very few facade-related events, at least in Asia Pacific and the Middle East, and even in Europe. So when we started this back in 2012, we were surprised why aren't there so many events on this topic where facades are, if not the most important part of the building, at least the most beautiful part, and there's lots that can be discussed in facades. So we've grown, and obviously we came to North America in 2016, predominantly with New York City, and then we've grown. We've done, 10 plus cities in North America itself. We've got a couple of events in Canada. New in Canada this year is Calgary. Again, we've been to Montreal, Vancouver, and Toronto a couple of times, but Calgary is another place where we are debuting in Canada. Of course, this year we don't have our South American events, but we've had a couple of editions in Mexico, in Sao Paulo, and Brazil. So yeah, all these events are designed these events are curated to that respective country. No two events are same. Every region has its own challenges. I think most of the Western world, Europe, is about adaptive reuse, embodied carbon, and heavy on sustainability. Most of the Middle East is about giga projects. So we have a mix of both. Today we have people who are talking about projects which is local to this region, as well as a couple of international projects. And our speakers are people who are architects, who are engineers, who are contractors, and they're going to be talking on a wide range of projects. So this is our 2026 lineup. We finished 3 events. We finished our 2 events in Australia a couple of weeks ago, and then we finished Barcelona last week. And we've got our first North American event for this year starts with DC. Again, these events are courtesy our event partners. All our associate partners have a tabletop display outside, so please do meet them in the networking breaks. Quickly take a moment to introduce all of them. Maybe you know what all of them do, but probably let you know. Alpolic is a Japanese company. Alpolic are the world leaders in ACM, aluminum composite material. So they are our first associate partner. Arcon Glass is from Germany, so they are a specialist in bird-friendly glass. Barbara J. Architectural Sales is a local rep from this area. She distributes a lot of cladding products, terracotta, which she's represented with NBK, and a couple of other non-combustible cladding products. Building Composites, again, a group company of HITT. You'll be hearing from them later. They have a new composite wall panel system. Cladding Corp, again, one of the rain screen system companies here in the US. They are distributing a Swiss-based fiber cement cladding product called Swiss Pearl. Cosentino is from Spain. Their cladding product is called Decton. Initially a product for kitchen top, which has now been engineered to be used on the external facade. Dry Design, a Kingspan company, metal rain screen cladding products. EJOT, a German company, they would be speaking later today. They are having fixing systems for ventilated facades. Equitone from Europe, they've got fiber cement cladding solutions. ES Group, one of the leading glass and glazing contractors based here in South America. EXO is a distributor of several European cladding products, and I believe they are launching a new clay-based cladding product, which is on display outside. Guardian Glass, again, need no introduction, one of the leading coated glass manufacturers globally. Hydro from Norway is one of the leading aluminum extruders. They've got recycled aluminum and a lot of other aluminum extrusion solutions. Jansen is from Switzerland. They would also be speaking later today. They have steel profiles for doors, windows, and curtain walls. Mouritzen is again another Kingspan Group company, metal rain screen cladding solutions. Safety First, one of the leading fire-rated glass and fire-rated systems provider from North America. SFS from Switzerland, rain screen cladding systems, attachments, and other accessories. Siderise is from the UK, from Wales. They have a pacifier product which is used for perimeter protection of the curtain wall and also for rain screen cladding. They also have a talk a little later in the day. Walker, again, one of the leading North American glass companies. They've got acid edge glass, bird protection, and other value-added glass. Zeef Panel Systems, metal rain screen systems. They are debuting with us for the first time at this event. And of course, we have our agenda partner, which is Enclose. Enclose is a leading specialty contractor based here in North America. So all of you will have an agenda on your table. So that has today's program for the day. And of course, our lanyard partner is Island Facades. You can scan their QR code on your lanyard. So Island's also one of the leading glazing contractors here in this region. Our next event in this region, we have Los Angeles, which is on the 9th of April next month, and Calgary to follow immediately after that. Then we have our two events in May, which is in Phoenix. First time, I think, facade specific event in Phoenix ever. So it's an interesting place. So let's see. And Vancouver, of course, is the third time around. We are coming back to Vancouver. So these are our next 4 events in the North American regions. Of course, we've got our biggest event in New York, which is on the 14th of October, and our biggest Canadian event is in Toronto, which is a week earlier on the 7th of October. So we've got lots of events happening across this region. And of course, I'm not part of the North American team, more part of the global team. So I get to go to most of these places, but we have a big calendar of events this year, 34 events in 19 countries this year alone, and all talking about facades, and it's all storytelling. You know, most of our speakers are only sharing their experiences and what they've done with either designing, engineering, or installing facades. I hope you'll enjoy today's conference program. We've recorded today's event, which means that if you miss any presentation, you can view it on the YouTube link, which will reach you a week from when we complete today's event. And that's it from me. I'd like to call upon today's event host and convener, Martina Driscoll. She was a speaker last time around at this edition, so she's going to be hosting today's event. She is from WJE. They are one of the leading facade engineering firms and building sciences firm based here in North America. So she's going to be taking you through until the end of the day. So that's it, and I hope you enjoy today's event. Thank you all.
Good morning, everyone. As Ahmed mentioned, I was a presenter last time, and now I'm an MC. I don't know if that's an evolution or devolution, but here I am. Thanks for coming. I have a couple small housekeeping notes. We have a coffee break and lunch hour to network and engage with each other and the exhibitors in the expo. Yeah, obviously, it's a great opportunity to see their materials up close. For any of us who have practiced in this space for any period of time, you know how important it is to have relationships with manufacturers and technical reps. So please take this opportunity to make some of those, to meet some of those people. And obviously, we thank them for their participation in today's event. The venue asks that you not bring lunch into the ballroom. Coffee, drinks, snacks, that's all okay. If you'd like a certificate of completion or continuing ed credits, there will be sign-up sheets at the end of the day in the expo. You do have to sign up on those sheets to receive either of those things. It's not automatic with registration or anything like that. We do ask that the speakers for each session return to the stage at the end of your session for a brief photo and a thanks from Zak. And with that, we'll start our first sessions. Just a note that we typically will not have time for Q&A during the sessions, but please reach out to the speakers either during breaks or after the event. I'm sure they'll be happy to answer any questions you have. And with that, I'd like to introduce our first speaker of the day with a project kind of near and dear to my heart as well. Colin MacKillop from Quinn Evans Architects will be speaking on the restoration and preservation of the National Air and Space Museum, just down the road from us here. Colin.
Thank you, Martina. Good morning, everyone. It's a pleasure to be here today with you to talk about the revitalization of the National Air and Space Museum. We could jump to the midpoint. It would go a lot faster, but I think we'll maybe take it from the top here. And thank you to the team at Zak World of Façades for putting this together. So yes, as Martina mentioned, this is for a presentation of the revitalization of Smithsonian's National Air and Space Museum. I just briefly introduced myself. I'm Colin MacKillop. As Martina mentioned, I'm a principal at Quinn Evans' Washington, D.C. office, and proud to tell you this story and to be part of this overall effort was quite extensive over the last 12 years. So with this project and ultimately this monumental effort, a collaborative team worked very closely to develop an integrated solution to address a number of very significant challenges with this iconic building on the National Mall. The project dates back to 2013 when we started the design phase, followed by a 7-year construction process, which was completed last summer, which basically involved the entire reconstruction of essentially the whole building, both interior and exterior, but ultimately to renew the facade among many other systems. So today's presentation will focus on the development of the new envelope and how that was developed to provide better protection for the galleries and the exhibits within that are among the most treasured artifacts of aerospace history and our nation's heritage, as well as certainly to improve the visitor experience. So with this agenda, we'll start off with just a brief overview of the history of the project and some of the many challenges involved and how that informed the project goals, and then focus more deeply on the development of the new stone-clad envelope and glazed curtain wall, and then we'll finish with a review of the north entrance pavilion. So the original building is comprised of 7 zones that alternates between stone-clad pavilions and glazed infill atrium galleries. The public museum spaces are on the first and second floor, including the large atrium galleries along the north side. There are offices for researchers to do their work on the top floor with support space and parking in the basement below. The site is really quite expansive and the equivalent of 3 city blocks spanning from 4th Street on the east to 7th Street on the west along the south side of the mall. So I'll show you some key dates with the development of the original building, which also provides a bit of foreshadowing for our project. The original building was authorized in 1966 with a budget of $40 million, but the funding for the project was not authorized until 1972 for that original budget and did not account for escalation. So essentially that amounts to a 25% reduction in the construction budget without the escalation that would have happened over the 6 prior years. So this required extensive redesign to deliver the project with essentially that lowered budget, and through which they integrated several progressive methods of construction. So among them, this is the first fast-track construction project taken on by the GSA, is constructed by by Gilbane to meet the very fixed deadline of July 1st, 1976 to celebrate the country's bicentennial. However, some of the other methods of construction were a bit less established with exemplars, and spoiler alert, not all of them worked out very well in the long run. Some of them didn't last very long, really, at all. But to the project team's credit, they delivered the building on time and on budget. But as the Smithsonian has said, they've been paying the price ever since. So, in terms of the the design of the building, it helped lead to a very successful delivery, and also how it was open to the public. It soon became one of the most visited museums in the country, and that's in part due to the original design concept developed by Guy Obata of HOK. He's the O of HOK. To display these artifacts in their natural habitat with the view of the sky above, which create for really dramatic spaces. But the problem is these exhibits, although they were originally fabricated to endure the elements, they were not intended to be displayed in daylight in perpetuity. So it ended up leading to a lot of damage over time, somewhat surprisingly. The original skylights you see in this image here are acrylic domes, to give you an idea of some of the budget cuts. So although it allowed them to meet the lowered budget, they weren't built to last. So those original skylights were replaced with tinted glazed skylights in 2001, but that issue of excessive exposure to daylight remained. Further, the envelope lacked a thermally broken frame. So the HVAC system for the building was established with set points of 70 degrees Fahrenheit and 50% relative humidity as a consistent interior environment to protect the exhibits per museum standards at the time. But with the lack of a thermally broken frame, that led to excessive condensation almost immediately after the building was open, to where reports were saying it was like the building was crying inside. And as a Commanders fan, I can kind of relate to that. So they turned the humidification off, but that unfortunately exposed these exhibits to less than ideal interior conditions. This is a great example of how the exhibits and these treasured artifacts of aerospace history were actually not intended to be displayed in daylight in perpetuity. So the Spirit of St. Louis, it looks like it's fabricated metal panels, but that's actually canvas with aluminum dope on a wood frame with steel tubes on the wings in order to reduce weight. There's actually no front window for this or seatbelt. So it was all to minimize the weight for the first solo nonstop transatlantic flight. So this exhibit was installed quite dramatically within the main atrium gallery suspended from above for many years, but in hindsight, it was said to be the equivalent of displaying the Mona Lisa under the skylight right by the front door. So part of our project was to make sure that we're protecting these exhibits while maintaining the historic character of the building. Certainly another key part of our project was to study the facade and understand what's going on there and how to fix that. So the project actually started with a feasibility study for the replacement of the HVAC system, which would reach the end of its usable life. That included a study of a vertical interior plenum that was part of the wall assembly. And certainly the stone as part of that assembly, which clearly something was going on there. So this original stone is Tennessee pink marble. So despite its name, it's actually a sedimentary stone, which is classified as a type of limestone. So with this image, you can see how it looked when we started our project in 2013. And although the basket weave appearance has become somewhat trendy, this was not intended. This is actually the result of thermodynamic hysteresis. So the stone was installed with only a 1 1/4 inch thickness, which was part of a progressive method at that time to be able to cut the stone that thin and install it in order to save money. On the back face of that stone was closed cell urethane foam insulation for the thermal barrier. That ended up trapping moisture on the back face of the stone and then further accelerating the hysteresis and causing it to bow out of plane. So with our project, this again was a comprehensive renovation, but in terms of the envelope, the project objectives were to restore the historic fabric of the museum, maintain its historic character, but replace the failing stone system, as well as the glazed curtain wall, while maintaining historic character with a thermally broken and blast-rated frame, while maintaining the existing footprint of the building. So with this diagram, to the left, you can see the original exterior wall assembly with the vertical plenum just inboard of the cladding that were just shown very thin with the spray insulation of varying thickness on the backside. To the right, you can see the new wall assembly as installed, which is essentially a conventional rain screen fastened to a curtain wall system of lightweight, thermally broken aluminum frame. And part of our challenge was the original structural frame was only, it had very limited reserve capacity as part of ultimate stress design developed by the structural engineer, William LeMessurier. So that limited what we could do as part of the new frame. So as we developed the details here of this fairly unique wall assembly, we studied this to help identify the predicted dew point within the wall section using WUFI and therm analysis to make sure that we were mitigating the risk of interior condensation with the reestablishment of the humidification. This system was ultimately installed with the E-clad system. So it's, again, thermally broken aluminum frames with 4-inch thick mineral wool insulation metal panels. We had developed that starting with the design assist process as we transitioned from this original version towards E-clad, with working with the construction management team of Clark, Smoot, Consigli, and their stone contractor, Rugo Stone. The WUFI analysis in this development was developed very closely with our envelope consultant, Simpson Gumpertz Hager, and we appreciate the peer review from Martina Driscoll and her team at Wisjeni Elsner, and we appreciate her support as the voice of reason as we move forward towards installation. So in terms of selecting the actual cladding material, we looked at over 120 different stone options because to install Tennessee pink, the original stone, but at the required thickness of 3 inches, would create significant issues in terms of the added weight, the cost, and availability. Among the other options, we looked into integrating the building integrated photovoltaics. You can see down here in the left-hand corner, but the Historic Preservation Office said that would not maintain the existing character of the building. Manufactured materials such as titanium and terracotta, shown on the right side, similarly would not maintain the appearance of the building. So as we looked into what type of stone would be used, we need to articulate what the performance or what the aesthetics requirements would be. And ultimately, this was defined as how it would be perceived from different distances. So from greater distance, the warm tone and a level of consistency helps express the monumentality of the overall scale. But as you approach the building, tonal variety helps modulate these planar facades for a more human scale. And then as you get even closer, the pattern of the stone emerges with greater visibility, with such as the linear veining of the original Tennessee pink marble. So ultimately, the selected stone was colonial rose granite, as determined through this very comprehensive process. It's installed at 2 inches thick. It's an igneous stone. It's very durable. It's a sandblasted finish, and there actually is linear veining with this granite. So we did a dry lay of this facade, 80 feet by 80 feet, in Cold Springs facility in Minnesota, and they're the supplier of stone. And working with Rugo and Clark, Smoot, and Consigli to articulate how many panels needed to have the pattern, at least 40%, what the range of tonal variety was, and that ended up being documented in the aesthetic requirements, but also to make sure that this could be delivered on site and on schedule. So this shows you the installation process. To the far left, this is the stone as installed at the west end in phase 2, left, right, this one. And next to that, you can see the granite as it's being installed with mast climbers. Next to that, you can see the insulated metal panels from the E-clad system, and then beyond that is the last facade of the Tennessee pink marble that remained. There are many theories as for what this pattern represented of the insulated metal panels, but it's essentially random. There wasn't a color specified for the insulated metal panels because it wasn't intended to be exposed beyond this temporary condition during installation. It's just whatever was available at the Kingspan plant in Ohio to meet the performance requirement per the spec. So this is the completed installation. As you can see how it meets the intent. It's got that subtly warm tone, but it's evident there's some tonal variety, and as you approach it, you can see greater detail as evidenced with, again, at least 40% of the panels with some markings that linear veining needed to be installed, no more than 45% relative to horizontal. That also helps tie in with the Tennessee pink panels that remain on the interior of the North Atrium Gallery. Next, and you can see through the curtain wall. So with the replacement of the curtain walls, we transition to this. You can see how the existing system at the time was failing as the gaskets were beginning to disengage, but also with the lack of a thermally broken frame or blast resistance or suitable protection for the exhibits, it ultimately required a system replacement. So to develop that system, we used an iterative process, again, working with WUFI and Therm, but also adding computational fluid dynamics to test the system to make sure that we were mitigating the risk of condensation. And as we found the results from this whole process, CFD analysis would go back to the beginning, tweak as needed until the performance requirements were met. So classic wash, rinse, repeat process there. So with the computational fluid dynamics, that was really helpful to make sure we understood the interior airflow and varying temperature conditions at various heights. This is a 60-foot tall curtain wall. And you can see, like, with some of the red here, those were fin tube radiators that were added as identified from some of the previous left, right, down. Well, you can kind of, sorry. There it is. So we had identified the need to add that those fin tube radiators to make sure that there was enough source of heat to resist the condensation. Otherwise, the temperatures are getting a bit too low. So with further development of the details, again, you can see some of the WUFI and Therm analysis here. What we found is that the triple glazing originally proposed for the glazed curtain wall could be reduced to double glazing and meet the performance requirements, but the triple glazing and the skylights need to be retained as such to meet that the requirement to avoid the risk of condensation, particularly above exhibits and with the visitors below. The selection of the glazing itself was another key part of this. So working very closely with the museum curators, they had wanted a maximum light exposure of 1,000 lux, which translates into 1% visible light transmittance if we were just using tinted glass. And that's basically 99% opaque and a glass box. A black box. So whereas the curators and the mechanical engineers would be perfectly happy with that outcome, it would not retain the existing character of the building as required. So what we're doing is developing a system that used 23% VLT, so it actually has more visible light transmittance from what was installed in 2001, and then applying a gradated frit pattern. So that starts at 12 feet above the ground floor level of the main galleries, transitions to 56 opacity, and then the upper half of this 60-foot tall curtain wall has that 56 opacity with the frit pattern extended across continuously with the skylight. So that the combination of 56% opacity frit and 23% VLT glazing is 10% combined VLT. However, that alone was not enough to meet a lux budget of $1,250. So thankfully, we were able to work with the conservators to, rather than work with a maximum exposure of 1,000 lux, it was a lux budget, so the average of 1,250 lux through the course of the year, including exposure to indirect daylight and artificial light, which can damage these exhibits. So in order to meet that requirement, we added a solar shading system within the space frame below the skylight. So what this shows is a fixed diagonal panel set within the space frame truss, and then operable horizontal roller shades, which can be adjusted for seasonal exposure to the sun. So on a day like today, with the spring equinox tomorrow morning, the operable roller shades only need to be deployed halfway. In the winter, when the sun angle is lower, those operable roller shades can be fully retracted, but in the summer to be fully deployed when the sun is high above. So these are shots from an animation that was developed for proof of concept to the curators, that there's an even distributed light without direct exposure to daylight, but still with a view to the sky above as seen from the concourse of the first and second floor. So as installed, you see that both from the interior and exterior, this maintains the historic character. And with this image, you can see how there's that consistent light level. So actually, the light levels are lower than the pre-project condition, but because it's more consistent, there's no glare. Actually, it feels lighter while also reducing solar heat gain and thus energy costs. So with this last part, talk briefly about the north entrance pavilion. So when the building originally opened, it was designed to anticipate 2 million visitors per year, but that quickly exceeded it towards an average of 7 million annual visitors. The original building only had 4 revolving doors at the entrance. In 2001, as part of that skylight replacement, a vestibule was added here, but unfortunately that didn't have enough depth to accommodate the physical security screening equipment that was added in 2006 per perimeter security process. So with our project, we needed to integrate not only these programmatic requirements for a better security screening process and better visitor experience. We also added accessible ramps at the entrance. We also, as the Smithsonian mentioned to us and suggested that the new entrance pavilion should express the mission of the museum, which is to commemorate, educate, and inspire. So for this, we looked into the galleries at Da Vinci's early flying machines inspired by nature, the Wright Flyer, First in Flight, America's Own with its taut light fabric and clean engineered details. And then working with the researchers whose office is on the top floor, appreciate the significance of the hyperbolic paraboloid, which combines the arc of escape and arc of infinity, which facilitate a deep space exploration. So this informed the details and the form of the canopy. So we worked together with our stellar team of design consultants, including T.Y. Lin, Muller, SGH, AECOM, and GHD, to develop these details. It also included a performance mock-up up at Intertech, working with Clark Smook and Sigley and their contractor for this scope, which is Roshman. And with this, you can see the installed and completed version. So the roof material is PTFE, which with a stainless steel gutter that routes stormwater through the steel frame into the basement, where it's filtered for irrigation and reuse and with other functions on site. That PTFE material, again, lightweight, durable, and fire resistant, but it was developed during the space race for the spacesuits that allowed NASA to win the space race to the moon. The first director of the museum was Michael Collins, who piloted Apollo 11 to the moon. He wore a PTFE spacesuit, and that's the material at the entrance to the building. So indeed, it was an honor to work on this once-in-a-generation project. And we hope you get a chance to visit the museum now that's fully revitalized. The remaining galleries are going to open July 1st of this year to celebrate the 50th anniversary of the building, and of course the 250th anniversary of the country. Thank you.
Our next speaker is Vicente Montes. He is a principal and facade engineer with Curtain Wall Design Consulting, and he's going to be talking about solar reflectivity, death rays, and such. So welcome, Vicente.
Thank you, Martina. Thank you very much. Good morning. How are you guys? I'm not going to do the typical thing. It's like, good morning, I didn't hear you. We're not doing that today. So I'm Vicente Montes. I'm with CDC. We are an envelope consulting company. We have been in business for over 50 years, and all that we have ever done is building envelope. We don't do mainframe structural engineering. We don't do anything else but building envelopes. So the topic that we're going to talk about today is when buildings attack their neighbors. And it kind of sounds like apocalyptical, and it is. You'll see. So with this photo, if you see here, there's some dead grass here in the middle of this road, and people were wondering what was happening, right? So this facade is west-facing, so all of the landscapers and everyone was coming in very early, trying to fertilize. They even replanted the grass. They did irrigation. They tried many different things, and nothing worked. But unfortunately for the landscapers, they were coming in very early in the morning. So when they left, before they left, this is what's happening. So you can see the reflections from the building coming in here later in the day. And voila, that's exactly what's happening. So that's what's killing the grass. Historically, and this is within the last 20 years, there's been many issues in different parts of the country where the death rate has happened. One of them, famous, is in Las Vegas. The very first one was the Walt Disney Concert Hall in Los Angeles. That one is Museum Tower in Dallas, Texas. And that one is the Walkie Talkie Tower in London. Now, we're going to go through the basic science behind how this works, how is this created, and then we're going to go through a few examples. Driving through any of the cities, this is something that you would see. This is in Doha, in Qatar. This could be like any random building that you can see. And then I was actually working on a project in Austin, Texas, and there was a guy sitting here by where the bicycle is, right there. And he had his beer in a koozie, because I guess that's what you do in Texas. You drink beer in a koozie. So he had his beer, and then all of a sudden the reflection started to move, right? And it got super hot, and the guy just had to go in, and he never came back out. So that Texan suffered, to a degree, what we're talking about today. This is in Barcelona, and this is in Dallas, Texas. This is an image from Google Earth. See how dramatic the reflections look. Now, fortunately enough, the reflections are perpendicular to the path of travel in this road, because otherwise, if you were driving into the reflection, that could be an issue to the people driving. This is what that same building looks like from the ground, and this is what the building, what the reflections that you can see while you're driving. So there's different things, different factors that cause reflectivity in buildings, right? Material properties, the location of the building, the orientation, the color of the materials, etc. But geometry plays a very, very major role. This is common. This is very limited space to build in urban areas, so this is going to happen. The good thing is that it can be prevented. There's three different types of glare. Direct glare is what you get when you're looking directly at the sun. Reflected glare is what you get from buildings. And disability glare is when you're looking directly into the glare and it blinds you for a few seconds. Now, thermal load. What you see here is the whole solar spectrum, and this is key. The portion of light that we see, that humans see, is only the visible light. Some animals and some other, with different devices, you can actually see light under this wavelength, and that is the infrared and the near infrared. But humans can't. Just regularly you can't. We only see the visible light. As you can see, the visible light fraction, which is down in the middle, that's the one that carries the most energy. But the other wavelengths also carry energy. So if you are not admitting this light through your buildings, you are reflecting it. And where does it go? So this is very important. Just in general, some glazing properties, if we're talking specifically about glass, we have transmittal, reflectance, U value, visible light transmission, which is how much of the light we're letting through, and solar heat gain coefficient, which basically is how much we're keeping within the building. And different coatings in glass are designed to allow certain wavelengths to pass through or to be rejected. Here down the middle, you can see, this is not working very well, so I'm gonna just walk. You can see this line is the line for the low E coatings. So the Lowy coating is designed to only allow the visible light to pass through the glass. The rest of the wavelengths are rejected. But again, where does that go? It's reflected back to the environment. That's what's happening in some of the cases that we're going to be seeing. Different coatings are designed for different purposes, and that's the lines that you see there. In general, if we're talking about an specular surface, then the laws of optics tells us that if we have a ray coming this way, the reflected ray is going to have the same angle, but in the opposite direction. We cannot expect that a ray is going to come in this way and then be reflected over there. That's just impossible. And then if the surface is rough, then it will be diffuse reflection, and that's pretty difficult to calculate. Now, something to consider. When you're selecting glass and you look at your glass properties, you see the reflectance coefficient. The reflectance coefficient is the data given to you by the manufacturers, and that's when you're looking directly into the glass, like perpendicular to the glass. If you move, if you are not directly into the glass and you move, the reflection of the glass increases. If you see on that graph, if you're looking at the glass at like 60, 70 degrees, that means that the glass just became like a mirror. So just consider that there's even the most transparent glass, the very clear, ultra clear glass will reflect at certain angles. And now the death ray. So I don't know the new generations, but a friend of mine told me that back in the day, not me, a friend of mine, that people would used to take a magnifying glass and burn insects. That's kind of cruel. I never did that, but this is pretty much what the death ray is. And that happened in Las Vegas. This hotel, the Vedara, is south-facing, is concave, and all of the rays are concentrated into a single focal point. Now, when you go to Las Vegas, if you go to Las Vegas, go to this hotel, you'll see it. And what happened was that, imagine like this guy, you're drinking, whatever it is that you're drinking, a mojito, a sangria, even a non-alcoholic option, all available. But this guy had his newspaper, and the newspaper that is given to you at the Vedara is wrapped in a plastic bag. So this guy took the newspaper out, set the plastic bag aside, and all of a sudden, the plastic bag catches on fire. So yes, this guy might have thought that it was the apocalypse or something like that, right? But it wasn't. It was the death ray caused by the Vedara. And then I took these photos. If you, when you take photos, the camera compensates for the contrast and everything. So these photos are quite not, don't make justice to what is really happening. If you're standing here in this focal point, the heat is so intense that you cannot stand there for more than a minute. It's super intense. Then the lawyer's way out from this issue is when you go out to the pool deck, you have to walk by this podium to get a towel. And before you get a towel, you have to read that. So yes, that's the lawyer's way out. Now, unfortunately for Rafael Vignoli, because it is his building, this happened again to another one of his buildings. And this is in London. This is the walkie-talkie tower. For this building, the issue is exacerbated because the concavity of the building is not only in one plane, it's in two planes. And now the streets in London are kind of dark, but with this building, they are not anymore. And this is what you can see. Now, allegedly, the building melted a bicycle seat, and it also burned that walk of mat. And of course, when it's hot, people are going to be cooking for some weird reason, but people cook. I don't know why. And then, of course, these guys had to get super up close there to see if it was real, but it was real. And also, the story has it that this Jaguar was parked in one of the streets nearby, and the guy who owned this car got an upgrade because that was caused by the building. This is what the building looks like. And on the photo on the right is what the building looks like now. They had to install shading devices to block off the reflections. Now, I asked my friend AI for a super dramatic picture of these, And this is what I got. 30 seconds. It's amazing. Now, the industry has no limits of how much is too much. It can be 30%, 40%, 2 times direct solar light. There's no limits. But the limits are kind of subjective because it depends on many things like age. The older you grow, the less tolerant to glare. Your eye colors. Darker eye colors can tolerate more of this reflected glare. Depends on the eyewear, depends on the contrast, like the streets in London, super dark, but then you step into the super bright light. And it also depends on scars. If you had like LASIK procedure, you don't tolerate reflected glare very much. And also, if you're like rocking the unibrow, do not fix that. Do not shave it. Do not do anything because it acts like a visor. So do it like Frida Kahlo. Some of the projects that we have been involved is this one. This is the Nasher building, the Nasher Museum Gallery and Gardens. That's on the left. On the right, that building, Museum Tower, was built a few years later after the Nasher was completed. The Nasher was designed by Renzo Piano, and it was designed with these egg crates, looks like egg crates on the ceiling to allow indirect sunlight to lead the galleries. But then, a few years later, with this Museum Tower building that is built exactly where these egg crate openings are, that's what you get. So this is before, and that's after. So we were hired to find a solution for that. And then Texans do things, and they build this thing that I don't know what it is. They call it the solar dish, and we were hired to make sure that it wasn't going to cause any issues with air traffic. So that's the Dallas Cowboys Stadium. So if you go there, you're going to see it. You'll take a picture, and I guess just save it, I guess. These are a few examples of the more recent projects that we have done. We are using a new tool now to do this analysis. And this is a casino in California. They were concerned, they have 5 sacred and ancient trees that they were concerned that the new buildings were gonna affect how they continue to survive. So we were hired to make sure that was still the case. So there's 2 different types of reflectance on this glass. As you can see, there's a few peaks there that are caused by the light reflected off the buildings. We saw an increase between 6% to 48% of direct sunlight in some areas. And just taking into account direct sunlight, we are at 1600. I don't know, I don't think that you can see that very clear, but 1600 is somewhere around here. Somewhere around there. So there are some peaks that are caused by the reflected light. And then this is what the image looks like, what the output looks like. You can see here that some of the reflections are getting to the base of the trees, and you can see it here on this pedestrian walkway. And this is a time lapse of what it looks like around one of the trees. Remember the laws of optics. So if the sun is moving this way, the reflections are going the opposite way. So that's why you see 210 and then going against counterclockwise. The reflections are going counterclockwise. But there you can see that there were some affected areas. Now, one of the options was a glass film. Yes, I know, we are in the consulting business. We know what glass film does to glass and to projects. Yes, we can talk about it later. But one of the options is a glass film. And with the glass film, you can see that image on the bottom shows the results with the glass films, which shows that all of these peaks were mitigated. Another project that we recently did is the Georgia hospital expansion. They kind of like just extruded or added more floors to one of the towers, and that's there. You see the representation of what the change was, and they wanted to make sure that that wasn't gonna be an issue to any of their neighbors. Here, the areas highlighted in pink saw an increase of 4%. The areas highlighted in pink here on this new image saw an increase of about 10%. And the areas highlighted in pink there saw an increase between 20 and 30%. Now, the parking garage, for example, is what you see here in this image, shows most of the reflections, most of the affected areas are there. You could use this tool to determine where to locate certain things, certain characteristics within your building. So for example, if the elevators were located in the middle of that elevation and you saw these results, then you can decide to perhaps move the elevators to the corner to where you are not affecting cars with the reflections. And then we saw an increase 20% roughly on all the grassed areas. So with this information, the horticulturists, the landscapers can pick what type of plants will survive better in this environment. And this information is given, or for those cases was given as a delta. So this is your direct sunlight, account for 1.5 or 2 point, or whatever the case may have been for the selection of the plants. And the last one, we have this Texas office building. As you can see, there's nothing special about this building. It's just a rectangle, and it's only 3 stories, and it has no architectural merit. But that's just my opinion. The glass on the building is 12% reflective, and there were some awnings that have a little more reflectance. But this building was actually melting cars. It is actually melting cars. So they wanted to know what to do, and they wanted to do what options they had for mitigation, right? So we conducted the study. We did this very simple sketch showing that the claims could be real, that the reflections were actually getting into these cars that were parked, and then the only way to actually quantify it was to either physically measure it or to run this. So we ran it, and this is what we found. The image here on the left shows the model assuming that the glass is perfectly flat. And I'm not talking about roller wave or anything like that, but just like flat. The image on the right-hand side shows some of the pillowing or oil canning that can happen on glass. So if you modify this oil canning, because it was happening in some of these pieces of glass, then we modeled with 5%, 7%, 10% angle, and the results change, dramatically change. And that's just a validation of how far the reflections go into the parking lot. The image on the left shows where the parking spots are and how far the reflections get. And then on the right-hand side, it shows the intensity. So it is real. I mean, and how can you say it's not when they're sending you videos of cars actually catching on fire? So of course it's real. So that's it about the history of the projects, some of the projects that we have done. So if you take away anything from this presentation, that would be that everything counts, not just the visible light. If you're picking your glass, selecting your glass, you have to take into consideration the entire light spectrum, because that's what burns things. So glass film could be an option. Other projects that we have done have changed the geometry of the buildings, have rearranged the orientation of the buildings to mitigate this issue. Geometry and orientation is key. And then the solar spectrum is all the light we cannot see is what gets us. And if you haven't read that book, read it, it's really good. And then you have to know that this issue can be avoided. We can design to avoid this issue because you don't want to be the next death rate that makes it to the news. So with that, I thank you very much. And there's no more time for questions because I kind of like talk over this. But thank you very much for your attention, and very nice to be here with you all.
Those death ray projects always make me think of another book, Lord of the Flies. I don't know if you guys... Next up, I'd like to welcome Robert Miller. He's the president of Jansen America, and he'll be talking about practical tips for sustainable architecture.
Thank you. Oops, I made some space there for you. Good morning, DC. My name was already thrown out there, so Robert Miller. I give you a little bit of a background to the presentation. First, I need the presentation up, and I need a clicker. But in the meantime, let me give you a little bit of a background. I was in an event a year ago. There was a panel discussion on sustainable architecture, and one of the architects said something I really liked. Basically, they kind of got in a heated discussion, right? And one of the guys goes, at the end of the day, we need to demystify a little bit the workload behind sustainable architecture. What we're really trying to do, at the end of the day, is we're still designing beautiful buildings, right? What we're really doing is adding a few more things on the to-do list so that those buildings can be built efficiently. They last a long time. And then when someone needs to do something to it in the future, they can do it easily with minimal disruption. I thought, well, okay, that's pretty interesting. I'm going to use that then as the structure for my presentation. Before I go too far, you need to know who we are. As I already mentioned, steel. 100-year-old steel company based in Switzerland. We sell steel frames into U.S. manufacturers, glaziers, who then put everything together, customize it, and install it. So everything I'm going to talk about also has then as a common denominator steel. And I like this building because it's a historical renovation. It's beautiful, but at the same time shows you some of the applications you can do with steel. Curves, nice radiuses, nice oversized entrances. But what I want to get to is historical building in London, assuming we can get there. And this one is called Battersea Power Plant. If you can picture in your mind a large pig floating over it, you basically have the album Pink Floyd Animals, which was kind of an iconic album when it came out. This was built in the 1920s. It was went live on 1933, in which time it then stayed for 50 years as a main power plant for London, till it was decommissioned in 1983, and then it basically sat there for many years, and they didn't know what to do with it at the end of the day. So it slowly dilapidated. They slowly decided to go ahead and, well, they were bouncing back and forth. But in 2012, an ownership group came in and decided that they would make a multi-use out of it, aligning with the government so that some of the historical parts were kept intact, but then it would be converted over into a multi-use facility. We were invited in to look at the windows. Right? So these windows that were done were 1920s, very beautiful, well done, and that was what they wanted to keep intact. Similar to what we heard in the first presentation about the museum, a similar situation that you had here in London. However, there's a slight thing. So what you see in the one picture on the left was the original. In all honesty, the engineers did a great time in the 1920s to make this happen with the technology that they had. Using modern innovations like thermal brake, you could get the thermal performance, but think about it like a thermal brake on steroids. Because where Battersea Power Plant is you've got, first of all, you're in London where there's nice rain. You're on one side, the Thames River. On the other side, you have a major highway. So you've got multiple factors to think about. And then putting a few more things beyond a thermal brake in there, like integrated weather strip, couple channels, we were basically able to get a good performance on thermal, on sound, and then also on air in order to kind of make it then much more comfortable for modern living standards for the people who are going to be living and working there. I would like to, and then by the way, from the windows, at least from a corporate point of view, we then went crazy on it. I mean, we've turned it into multiple applications. We've turned it into multiple materials, steel, stainless steel, corten, and this year brass. Also, many of the different things you can do from curvatures, these have all been at least applied to multiple facilities in the past. I'm having to go a little bit fast because of the time frame. Before I jump into building certifications, let's even see if I could come back, and I can't. What I wanted to mention in one comment is a good tip. Remember when the architects were talking about making it easy for people in the future who have to do renovations? It's a very small thing. It really has very little to do with us as a company, but it does have something to do with just overall planning. Think about someone who's going to dismantle this stuff in 50 to 100 years from now, and a lot of it comes down to connections. So if you're welding that stuff together, it's actually going to be nearly impossible. The only way you can unweld something is simply cutting it. But there's also multiple ways you can do it. Screwing, there's multiple assembly and disassembly. And then the irony is, by making it easier for somebody 50 to 100 years from now to disassemble it, you're actually kind of making it easy for the person to assemble it now. So you're also hitting two birds with one stone because it's easier to install, easier to deinstall, and it really doesn't have much of an impact on cost. Just wanted to kind of throw that in one of my little practical tips to try to help. For building certifications, I want to start with a little bit of a holistic view. First, there's BREEAM. BREEAM is more relevant perhaps in Europe. They are UK-based, but they do have an office here in California, pretty much trying to accomplish very similar things to LEED, where they're looking at a building, certifying it, and making it efficient. And my legal caveat, similar to what we heard a legal caveat earlier about the sunbathing, anytime you talk about building certifications in front of a bunch of architects, definitely there's a lot of people in the room who know a lot about this topic, and some people who may be hearing it for the first time. So we're going to start with a little bit of a high view and then kind of work into some of the details. Beyond BREEAM, let's go into the details of a second one. It's called WELL. And I really like WELL because WELL is looking at certification of a building, but looking at it from the perspective of the inhabitants that are in the building. So there is something called building sickness, and it is probably not an overall coincidence, right? The amount of technology that's put in a building, the Internet of Things. So this is looking at how can we do innovation? How can we certify a building to be really high performance, but keep in mind the people that are in that building? Then, of course, you have the main one, which is LEED. The way LEED works is that you have multiple options or certifications that you strive for. Which one you strive for is really a discussion with the building owner, what makes sense for them and what they're trying to accomplish with the building for the ROI. And then each of these is based on a point system, right? And that point system comes down to multiple categories. And what's interesting now, and why is a person who with steel talking about this? At the end of the day, materials and building materials, all of us that are out there presenting or talking in general, we're not part of the certification, but definitely building materials make up the building certification to a certain extent. We directly or indirectly influence a lot of that. From our calculation, things like steel would impact about 56% of it. So this is a report that we did in Europe. What I've done for the United States is take this report, but also then highlight it in not just a nice shade of green to make it slightly different, but to also highlight where there's direct and indirect performance values. And what you can see is 56% is actually impacted. And let's look at why that 56% is impacted. Sorry. I'm going a little bit too fast because I have a lot that I'm trying to be excited and share with you. But let's look at this one here, this energy and atmosphere. Energy and atmosphere at 30% is basically the operational performance of the building, right? And why is 30% one of the key ones, and where is there a direct correlation? It comes down to longevity, things that last a long time, of which 75 years for doors, windows, 100 for facades, for example, is not a far cry. Remember, the Battersea project was 1920s, and we looked at it, and the engineering was great. They just didn't have necessarily some of the innovations we have today, but those things lasted a long time. The other thing you have with steel is something that's continually recyclable. So basically, if you recycle something like aluminum, you're basically going from big to smaller, to smaller, to smaller each time it's recycled. And with steel, you're able to keep roughly the same size, and you're able to keep a certain amount of strength to it, which makes it very valuable for reuse. So making that point yet again, you can see here some studies that we've done in Europe in which we compared ourselves to not just aluminum in general, but premium aluminum. And then we also went so far as a green steel approach, which is basically where we're buying recycled steel and using that as the core basis of our profiles. So in short, the contribution that steel can make is high thermal performance, means less operational carbon. The noise reduction, light, means an improvement there on wellness. The strength of it behind means that it can be constructed efficiently using less materials and less embodied carbon. Long lasting. And low embodied carbon when steel, but also with green steel, which is recycled steel coming from our suppliers. Recycling with strength retention and adaptive reuse. So I tried to crank all of this out in 10 minutes. We do have our own reports, which we have done together with independent consulting company in Germany. I'm happy to say that we just released them in the United States last month, and we are also outside. Brief comment only on the fact that there are LCAs, EPDs, all of these other things as well, but I'm going to skip all of that at the end of the day and pass it on now to the next speaker. But thank you very much, Washington, and if you have any questions, we're happy to talk to you later. Thank you.
All right. Our next speakers and our final speakers before our first break are Reginald Truxon. He's a senior associate with Gensler. Dean Mouritzen, he's a project executive at HITT.
Yes.
And Andy Loff, he's CEO of Building Composites, and they'll be talking about HITT's new headquarters in Virginia.
Sure. Good? Yeah? Is that good? Yeah. Okay. Thank you. All right.
There's our lead off, man.
Sorry I'm late, everybody.
You can also highlight.
Yeah.
There you go.
All right, good morning, everybody. Thanks for joining us today. My name is Dean Mouritzen. I'm the project executive for HITT Contracting. I'm overseeing our new build of our new headquarters in Falls Church, Virginia. We're here today to discuss. I'm actually excited here today to discuss about a little bit more about a headquarters, what initiatives we have that we've implemented in the headquarters, as well as the facade strategy associated that's shaping the building that you see on the screen. The project is actually in Falls Church, Virginia. It's a few miles away from here. This is going to be our new home, and it's also a hub for innovation for construction. We're bringing together, workplace research, collaboration, and an industry under one roof. I'm going to go next. So here today behind me are two magicians that have actually made this product, the Hyperwall product, successful. Andy Loff is the CEO of Building Composites. He's the brains behind the material makeup of the panel. And Reggie Truxon is the design manager for Gensler, who was instrumental in the design of the actual Hyperwall panel. Before we get started in the technicalities, I just wanted to talk through the core idea of the building. We were able to use this building to be able to actually try to solve real world problems from labor shortages, rising costs, and definitely the need to make things more efficient and more structured in the workplace. There are four focus areas for us in the building. So the one need was to be able to create a collaborative space for our workforce, to be able to, learn, to engage, to, have well-being, enhanceable experiences for the team members inside the building. We're using this building to accelerate our research and development initiative, testing advanced technologies, materials, and also construction strategies within the building. And we're also we've engaged more with our partners, our trade contractors, all the manufacturers, and also academia to enhance that innovation of construction through this project build. And obviously just evolving new technologies. We're implementing new technologies and evolving the business of construction. So what you see here is the rendering of the building. It's not just a traditional building for us. It is a 270,000 square foot, 6-story office building. This is where construction magic is going to happen for the foreseeable future. We have multiple R&D initiatives in place now during the project build. Some examples are implementing prefabricated bathrooms, implementing prefabricated elevators. We even have a virtual superintendent Yes, we've got robots in concert with humans, AIs here. So we're utilizing testing that in this facility too. One of our main goals is a net zero initiative. So we've invested heavily in sustainable and innovative technologies in the building. You can see up on above the building is a 115,000 square foot solar array. We also have, which you don't see in the image, 4 wind turbines generating the energy necessary to power the building. We have 4 vanadium flow batteries in the basement that are going to store the energy, and we've invested in advanced cost savings PoE systems for both lighting and power. Normally it's, you've seen lighting, but we actually are implementing some power strategies too. And most importantly, what we're here today to talk about is the facade. So that has been instrumental in the vision and the look of the whole entire building. So with that, I'm going to pass it over to Reggie. Reggie is going to talk to everybody about the architectural strategy around the project.
Thanks, Dean. Okay, great. Well, thanks again, Dean, for the introduction. And it's a pleasure to be here with everyone. Again, my name is Reggie Truxon, architect and design manager for Gensler. And of course, with this HITT headquarters, what is a great benefit is not only having the headquarters and its innovation, but also across the street on the site, which is shown in dark blue, is Converge Residential. We had the pleasure to work with HITT and Rushmark on the design of both, and you'll see why it makes a difference having both buildings there to really explore. But as we know, design comes in a lot of different ways and a lot of different fashions. This is actually an image of the first iteration of this HITT headquarters. And the reason why I showed this is because this is the evolution of design when we think about hyperwall. Or sometimes we refer to it as PBS, as prefabricated building systems, but hyperwall formally is that skin system that we know we are dreaming and thinking of and actually bringing to reality of a system that can really quickly innovate and swiftly get the skin system onto the building. And so in this iteration, you can see these horizontal panels, these kind of nubs at the end of the panels, which we're really trying to express how this would, like the hoisting hooks and things of that sort. And so, as Dean mentioned, there were a lot of initiatives and a lot of thoughts. And one of the taglines was the result to have a better building in months and not years. And so we were thinking about energy production and dreaming big. There are many more than what's on this page, but as Dean mentioned, hyperwall, the skin system, is the one we'll really dig into today. And so as we developed this from the beginning, we knew we were going to go with steel because some of the structure of the wood was really thinking of the planking, but needless to say, in the first iteration, we were really fastening these hyperwall panels at the columns, and that was the limitation that we established first. And that really drove the width because we know in office buildings, our 40-foot width is something that we want to hold on to because we know that's going to play into a great building. And so this kind of section in Axon shows that 13.6 floor to floor also is a critical dimension that I know Andy will go in a little bit more as far as the shipping of the panels, but we know that we were confident that we can make a strong and really successful building with this section. But as we went through the iterations of the hyperwall panel, you can see starting with the standard configuration with a 2-foot border on the top, a 1-foot or a 2-foot border on the bottom with 1 foot 4 verticals. This was the initial take and the initial pass because that is what the frame system could handle. And so we played with that a little bit more and going to the second iteration of saying, well, what if we wanted some depth? Let's add on some of the fiberglass to really add some additional extrusions to give a little bit of variety to the facade. Okay, now we're going to play some more what ifs. What if we wanted to create the module of these windows in a little bit stronger, succinct, and standard module of smaller windows, smaller panels so that they can be reproduced. But then also, what if we thinned that up, that 1 foot 4 limitation? We don't really love that. Let's try to get that down to a foot if we can. And we were successful in that. And then the last iteration is saying, reality is that we probably can't get the building to be all hyperwall at all times. So we need to automatically think, okay, we're going to have a combination of hyperwall and curtain wall in some locations. And you'll see that in some of the renderings as well. But the last thing that critical to what you'll see into the building that is today is we were going horizontal knowing that we had to go column to column. Can we go vertical? Can we think of this as a vertical module that can go now 2 stories in height and not have to connect to the columns and connect mid-slab? And what you'll see is the lightness of that panel and the lightness of the glass was what enabled us to get to this. And of course, we reduced the whole frame into that 1 foot profile because why not? In this iteration, we are looking at 3 panels across the 40-foot module, about 13'6". And so that was really the first iteration. And so, of course, we're going to design, and it's great to have great partners with HITT who really loved going through this research and development for this panels. And so I'll go through a couple of these schemes, and you'll see the progression of what it led to. So looking at this first scheme, which is the standard module, which is from column to column, the 40-foot. This one specifically is actually adding 1 fiberglass profile to the panel, which could either be molded or added onto. That's what had been researched in this. The second version and second iteration here is going to that secondary module where we reduced the size of the window walls and the size of the windows, but we also added another metal panel, a corrugated metal, to say, hey, what if we change the materiality? Could we really vary some of the texture and the finesse of the building? And in this third iteration, which is ultimately where we really started developing that we love the most, created this really glassy building structure with this showing that 40-foot module and that 2-story. And so here's that iteration with the window wall system inside the frame of that fiberglass frame. And so if you look all the way down through schemes 5 and 6, you'll see scheme 5 is like, okay, let's play with the proportions a little bit. If we go from 40-foot with 3 panels to 40-foot with 2 panels, okay, it makes a little slender of a profile. But then for scheme 6, what if we played this a little bit back and forth and tried to offset these panels? Now, ultimately, we did not go in the direction of scheme 6 of really offsetting to create the panels to create the variation in the facade. However, what we did was we took within the fiberglass and in the window wall system and add an extrusion. So every other panel has this extrusion to create this offsetting, which you can see in that center elevation. Also in this section, what we're really trying to show is we are going to create a really fantastic office environment, not just for the sake of research and development, but for the sake of the project goals, which is to enhance the environment for research for HITT contracting. And so what is a facade conversation and facade conference without some details and some type of technical understanding? This detail here is that section detail, really showing all the parts and pieces with in the center, showing or at least to the left-hand side of the detail, showing the hyperwall panel as well as the window wall system that comes in with it. But the typical systems on the right hand, the barrier wall system is really what this is showing, that it will feel the same. It will be the same in the environment. And so that it will not create something that feels foreign. And then likewise, again, this plan detail showing where those connections live within that furred area in that slab. And these 2 connection details is showing that push-pull connection, which is at the top and bottom. In this detail, this is in the center of the panel on that mid-floor, which is the gravity connection, which is actually holding the weight of the panel for this 2-story panel. But again, what are we talking about? When we look at and think about this complex, we're not only talking about the office building, we also have some of the learned lessons that we can take to the office and bring it to the residential building. So the residential building will actually be, which is shown on this slide, is going to be the horizontal panels, but you can see where the residential module has the smaller windows in a mix of larger areas of solid for the hyperwall to express itself. Additionally, on the right-hand side of the page, we looked at recessing some of the hyperwall and actually not necessarily applied of of material, but using the formwork to create some depth in the panel, which is being built and constructed now. And so overall, looking at the kind of the residential massing with the office building in the front, the vertical panels in the front and the horizontal on the side, and one more look at the residential where we have the two depth panels on that lower wing on the lighter side with the office in the foreground. And so really, this is an exciting project. We have great partnerships. HITT has been with us all the way. They have pushed us in the design of this building to create a really great environment. But I'd like to bring on Andy to tell you a little bit more about the hyperwall facade and the nuts and bolts of hyperwall. Thanks, everybody.
Thanks, Reggie. Oh, I don't need that. Where's my... Yep. All right, so I'm going to back up a second and kind of go through, well, what is the hyperwall? We talked about the design iterations, but we'll go through some specifics here on what is the system. Really, what we, and I'll talk about what it's made from and why it's innovative and interesting. So this project, or this whole construct, started with about a 4-year R&D project where we set out to ask ourselves or answer 3 questions. How do we enclose a building faster? How do we reduce the on-site labor? And how do we simplify the coordination amongst the various trades? And this really led us on this 4-year R&D journey where we even built a 40-foot by 80-foot 2-story building just to demonstrate these different 8 technologies, how they worked, how they installed, things we liked about them, things we didn't. And that really evolved into what we branded as the Hyperwall system, which in its current form is really actually very simple. It's basically just a fiberglass sandwich panel, as we call it. So you have fiberglass skins, shear webs, and foam. So it's really 3 materials. There's thermoset resin, fiberglass, and that closed cell foam. And then those are combined in a clever way that allows us to meet all of the life safety requirements and flammability requirements. But the concept of it is very similar. The way I like to articulate this is it's very similar to architectural or insulated precast in some respects. It's one monolithic cast unit. Obviously, we're about 80% lighter than the equivalent architectural precast, which changes the dynamic of the install a lot. But it's really not that complicated. And these materials have been around for a long, long time. I mean, things from wind blades are made with the same technology. Yachts are made with the same technology. The Boeing Dreamliners are made with the same technology. So the technology behind this is not new. And then this slide I put in here just because the Hyperwall can really come in many forms. So what Reggie was talking about was more of the office residential facade buildings, but the same technology we use for like mission critical applications, which this would be an example of an insulated precast replacement to do the same function, just at 80% lighter weight. And typically our panel sizes are really limited by the shipping constraints. So we don't really have if we wanted technologically to make a 50-foot by 400-foot panel, the technology exists to do that, I just can't ship it. And this starts to get into the Converge HQ panel, which is, or the HITT HQ project, which is pretty cool because it's actually being installed right now. They're actually installing some of these panels on the building today. So what we do with this is we partnered with Momentum Glass. They're the glazer that did these large format glass systems. So this panel right here, just to give you a scale, the glass pane in here is about 20 foot by 8 foot and 1 9/16 inch thick glass. So we're pre-glazing that in the facility, connecting that, caulking it, and then we load the trucks and ship them out to the site ready to hang on the building. And you can see some of the other features. This particular one is painted, so it has a fluoropolymer coating similar to what you would do with glazing. systems, same types of mica-filled or solid color systems that you would use on glazing. We have a solvent-based fluoropolymer that we put on the surface of these panels. So you get the same color fades and things that we're accustomed to. Then one of the coolest parts, the way we actually install these panels is with suction cups. Because as Reggie talked about, I'm more of a utilitarian person that likes to make communist-style buildings where everything looks the same. So we have a funny joke. We started off with nice horizontal panels and then ended up with vertical. But we ended up solving that problem. It was actually a really good collaboration. But one of the problems that vertical orientation gives you is you have to be able to turn the panels from horizontal to vertical because you have to ship them horizontally. And with the large format glass, that's actually really difficult to trip that vertically with a crane. Whereas the panels are light enough weight that we're able to just suction cup to the face of the panel and rotate them. I have a few more pictures of that later. This is just another illustration from the Converge Westfalls, the residential project next door. And Reggie talked a little bit about this. This is a multi-depth panel, multiple colors. One of the other cool things is we can really attach anything we want to the outside. So this one's pretty innovative in that balcony system is actually attached to the hyperwall panel, not to the building frame, which creates a lot of advantages from a detailing perspective because we're able to control the control layers all on the outside, pre-assemble this on the ground, and then fly it up and hang it on the building. And then this one we put in here just, people sometimes get confused on what we're talking about. But from an architectural perspective, you have this construct of the perfect wall, right? Like these are the orders you're supposed to put things in, and this is what's kind of taught in architecture classes and things. This is what we're replacing on the right. Basically, we're taking everything out of the equation except for the service stud wall and interior finish. And that interior service stud wall does two things. One, it allows us to run the MEP, but it also helps us bolster up the sound transmission reduction. So our typical offering for this is usually like an OITC of 47 or better, because one of the things that fiberglass does is really well with high frequency noise, and your stud wall on the inside does well with low frequency noise. So that net's actually a really high-end sound reduction system. These are some more pictures from the factory. You can see here, these are panels being loaded on the trucks. So we have these Conestoga trailers with double A-frames. So similar to a glass hauler, except for we put two of them on there so we can get more panels on a truck. So in this case, there's 8 of these panels being shipped out on one truck, and then the tarp retracts over it to protect it from road damage and things like that. And then this is in the field, some illustrations of how these panels are lifted and moved. You can see the suction cup grabbing those, and then the rotator rotates it into the vertical position, which then allows us to fly it over and basically hang it on the side of the building. And like Reggie touched on, a lot of the connections for this are very similar to curtain wall. They're, the picture hanger styles. We developed a little bit heavier duty version because our panels are so big, but the concept is the same. It has jack bolts and adjustability and things like that. And then this is a picture of that first panel going on the building. And as you can see, they'll work their way, around and up the building the same way. So every one of these panels, I think there's 351 panels similar to this on the building, including like there's some molded corners and things like that go on this as well. So yeah, with that, I'll turn it back over to Dean.
Test.
Just grab.
You good? Yep. So wanted to talk about the logistics on site and also the erection, or how we're erecting the panels at the headquarters. I'm going to show you just a couple of images of the renderings, but while I'm showing you, we'll be talking about the logistics part. But The plan is for just-in-time delivery. We will have 2 truckloads. Each truckload will have, like Andy had mentioned, on average, about 8 panels per truck. The goal is to install up to 16 panels a day, depending on the size. The initiative is to try and double the time, to make it shorter by half from an initial, from a like-kind precast panel, because the precast is so much heavier. So that is a huge, obviously time savings. The goal is to wrap the building in about 30 days for 350 panels. We have some ramp up, or we've had some ramp up time in the field already, and so now it's, we've learned some lessons, and we are now going to be starting about, averaging hopefully about 16 panels a day. Like Andy had mentioned, the two connections, how we're erecting the headquarters, is we're using that suction cup to be able to take it from the truck, rotate 90 degrees, and install on the building. On the residential side, we didn't need to have that suction cup, so we're just using standard lifting eyes on the side of the panels. From efficiency and a labor standpoint, now because we've taken that prefabrication process off-site, we've really minimized the crew size to a very small handful of folks on the site installing these panels. And because the panels taken away the follow-on trades for the air vapor barrier, the water barrier, those sort of type trades, insulation, we've now lessened the amount of folks on site, and we can actually see that today. The job site has become a lot more safer and more efficient and proficient for the other trades on the site. So it's allowed us to lessen the congestion on the project. So I think from a summary standpoint of this building, the hyperwall is the value of that hyperwall is it's just basically it's in its simplicity. We're allowed to, we can efficiently get a building envelope on a building. It's not become cumbersome on the job site anymore. It's now just, it allows us to concentrate on other things that are a little bit more cumbersome on a typical project. And that's allowed us to be able, sorry, I'll get back. That's allowed us to be able to think about other ways to be able to make the building envelope construction more efficient and smarter ways to do things. So with that said, I'd like to thank everybody for the time. We do have, well, I guess Andy does have a booth out in the front. If you have any questions about the hyperwall panel or additional questions, reach out. Andrew is the cohort for Andy. He's out there at the table. So any questions that you may have, please feel free to go over. We do have a site tour scheduled tomorrow at 10 a.m. For those of you who have not signed up and want to see the panel in person, by all means, speak to Andrew at the booth, and he can get you on the list for tomorrow. But thanks everybody. Appreciate your time.
So enjoy your break. If you could be back in the room in about 30 minutes, we'll get started again. Thanks.
That is Dan Gordon. He's fire protection engineer, which is Jansen, what she used. And they'll be talking about fire testing of the complete exterior wall assembly, not just the compound.
Well, thank you very much. Once again, my name is Dan Martin. I've been Jansen. Thank you to Zach for inviting me here today. I'm going to talk to you today about fire testing and where we come from. The building goes into fire testing our exterior wall assemblies, a little bit about what those tests are, and then kind of getting into how the components matter. It is an assembly test when we look at exterior walls. I was looking outside as I was walking through the various booths. I saw a lot of names of the sponsors and those of the booths that we've worked with in the past at Jensen years, especially with NBA 285 exterior wall flame spray testing. So it's good to see you all here. So some big old disclaimer. So we're going to go through a little objectives real quick, a little intro on the company itself. Look at some of the standards that we have to worry about with exterior walls. we'll do a little bit deeper dive with FPA 285 instead of it's a big scary exterior wall flake shred test that everyone has to worry about in that some impacts on the butt substitutions. So we're going to identify those standardized tests that relate to the exterior walls and where they come from in the code. We're going to look at that vertical and lateral flame spread test at FPA 285 and then understand the substitution of materials. So just to use by the numbers. So when you look at all our companies, we've been around since 1939. We're a life safety and fire protection engineering specialty firm. We also do physical security consulting, accessibility consulting.
So everything ranging from sprinkler and fire alarm to actually how do we build the buildings, how do we do egress with that. So we are a global entity. We have offices in the Middle East, Southeast Asia, Australia, New Zealand, the UK, and Europe, and Canada, and the US. So we do co-consulting, fire engineering, system design. We do a lot of emerging hazards, energy storage systems. Guess what? They're becoming more and more popular in your buildings as an architect, and the codes are ever changing when it comes to what level of protection you need. So we've got teams that are actually blowing up and burning ESS systems to understand to make sure that we have the proper vent capacity. Forensics, emergency response. So a little bit about me real quick. Senior fire protection engineer. I've been with Jansen Hughes for almost 11 years. I am a fire investigator as well. I'm part of our materials testing and evaluation team, so I get paid to burn stuff. It's one of the coolest jobs you never heard of. I literally get to burn stuff for a living. On top of that, I am involved in the NFPA committee process, ASTM fire test standards, and then I'm also part of the ICC code development process. So anybody going to be in Hartford, Connecticut in April as we finish 2027 codes? No? Okay, just me. Just the code junkies. So when it comes to exterior wall fire tests, where do we start looking? Well, our main chapters that we work with in the IBC are going to be Chapter 7, Chapter 14, a little bit in Chapter 15 because of the mechanical penthouse exterior wall situations, but then also Chapter 26. Chapter 7 is your fire resistance. Chapter 14 is your exterior walls. 15 is rooftop structures and roofing, and then 26 is your foam plastic insulation materials. Just your plastics in general land in 26. So right off the bat, top to bottom, fire resistance. How close are our buildings together? Does this need to be a 1-hour wall? Does it need to be a 2-hour fire rated wall? Do I only need to rate it from the inside, or do I need to rate it from the outside only? And can I have unprotected openings or not? So how do we evaluate that wall? What fire test do we use to understand that fire resistance once we get into that building separation distance? Vertical and lateral flame spread. We want to make sure that we're containing the fire and it doesn't go 30, 40, 50 stories up the outside of the building. So NFPA 285 is that vertical and lateral flame spread test that is referenced in 14, 15, and 26 of the IBC. Ignition resistance. I don't want to fire from a building across the way or on a really close lot line to ignite the facade material of the building next door. So there's requirements in the code with regards to that ignition resistance of those veneer materials. Perimeter fire barrier systems. So you're in the building, you have a fire on this floor. Well, we don't want the fire to go to the floor above when we have that edge of slab condition and your curtain wall or your exterior wall that's hanging off the edge. So ASTM 2307 is the test we use for that. Obviously, penetration fire stop systems. If we're going through the exterior wall, we want to make sure that we're fire caulking those when it's fire resistance rated. Now, there are some changes in the code coming up in the 2027 that if you're allowed unprotected openings, you might not need to do that anymore. So keep an eye out with the 27 codes because those rated exterior wall situations are changing. And then obviously you get into your rated doors and your dampers and your windows when you have those fire resistance rated assemblies, and those all have their own different test standards. So I'm going to tailor that down, and I'm only going to look at about 3 fire test standards. So ASTM E119 is what you have here on the screen. Basically, you build a 10 by 10 or a 12 by 12 wall and slap it onto a furnace. And that furnace reaches 1,000 degrees in 5 minutes and then tapers up to 15, 16, 1,700 degrees Fahrenheit, depending on how long you need it. Do you need a 1-hour wall, 2, 3, 4 hours? With this, if you are a symmetric wall design, you only need to test it one way. But if you have an asymmetric design and you need it rated both ways, you're going to have to flip it around and test it both ways. So you see those white squares on the back side, those are the thermocouple pads. And that's what we're measuring the temperature on the back side of that wall. The test standard gives us that criteria. Once we reach those limits, you've reached your time. Obviously, at the end of each test, we call the hose stream test, which is part of that. I don't have a good picture of it, but this middle section, you'll have this burning wall pulled off your furnace, and you're hitting with a hose stream. And you're making sure that you're not penetrating through that wall. It's a legacy test. ASTM Me-119 has been around for over 100 years, and we're still using it today. ASTM 2307, that perimeter fire barrier test, basically what we are evaluating is this joint right here between the edge of slab and the curtain wall to make sure that fire does not get up and in and to the floor above. So a lot of the curtain wall systems, you see that mineral safing systems where they put it in the curtain wall system itself, and then between the edge of slab, they put in compressed mineral wool and then put some sort of sealant over the top. You have a fire down below, and I'll get to that because it's the same apparatus we use for NFPA 285. You got a room burner fire, and then you have the exterior window burner. NFPA 285 is that exterior flame spread test. You can see that we have the room fire down below, two-story apparatus, and then we have the window burner. We're trying to control and limit that vertical and lateral flame spread. So NFPA 285, especially after some of the recent fires we've had globally with exterior facades, it's become a hot button item like, well, what are we doing here in the States? What are we doing here in the States? I can tell you, we've been back in the late 1970s, we started investigating this problem as fire engineers and combustible component manufacturers. Late 1970s, there was a Federal Trade Commission ruling that we needed to address this issue. The foam plastics industry, they took the lead on it. And the first test, full-scale test, two-story outdoor test, happened in the early 80s as UBC 176. Exterior wall flame spread has been in the code since the 80s and has evolved over the years. It was NFPA 285 in 2000 when IBC said if you have a test standard, it needs to go through the consensus process and it also needs to be in mandatory language. UBC 269 was rewritten to NFPA 285. So what is it? It's a multi-story apparatus. So you have two levels in here. You got a burn room on the bottom, open room on top, and you've got your sample that slides up against it. You got the fire coming out below, window burner on the outside to simulate a post flashover, completely room involved with flames blowing out the window. So your test sample is about 18 feet tall, 14 feet wide, and it represents the construction that you're going to use in the field. Interior JIT board, steel studs, stud cavity installation, exterior sheathing, water-resistant barrier, continuous insulation, attachment system, veneer. We are testing the entire cross-section, including the header and jambs of your wall openings with this test. So when I say this is a complete assembly test, we are looking at everything. When you look at the exterior wall flame spread tests around the world, they're mainly just looking at the facade. They built it up on a CMU or concrete wall, put the fire underneath it, and see what happens with the facade. This is one of the only tests in the world that it looks at the entire wall assembly. So if I put spray foam in this stud cavity, some other tests are not going to evaluate that because they only look at the facade. So you have gas burners down at the bottom and gas burners at the window openings to give you that simulated flashover. So what are we looking for when we run this test? It is a pass-fail test. It's mainly done with temperature measurements because obviously inside the wall cavity or inside that ventilation space behind the rain screen or inside the foam, you can't see visually from the outside. So we have temperature probes, about 50 to 80 of them, depending on the configuration inside of it with temperature thresholds. You're limited to vertical 10 feet of flame spread and laterally 5 feet to either side. You also have to prevent fire from getting into the second story above. Now, it is not exactly like the perimeter fire barrier test requirements. This is a 30-minute test. We're not doing multi-hour tests like those rated perimeter fire barrier systems. We just want to make sure fire doesn't get into the wall, up through the stud cavities, and then breach back through during that 30-minute period. And then we visually look at flame spread up and out. So we do the consulting on the front end with the manufacturers, developing their tested assemblies, helping them with that, witnessing the testing, and then doing the analysis on the back end. What can we get out of this tested assembly we just did? Can I change the base wall construction? I tested steel stud and gyp. Well, now it's a masonry wall. How do I do the technical justification for that? Or I need to change the type of insulation I'm using on the outside. The tested assembly used it EPS, but I want to use mineral wool. There are certain things that we can do based on the test, additional testing, and our testing experience to be like, okay, I can make this modification and maintain compliance with NFPA 285. When you look at the code says you need to run an NFPA 285 test on your exact system. But through Chapter 1, with alternate means and methods, you can have an engineering analysis performed and demonstrate compliance with NFPA 285. So there's things we can change in the exterior wall based on multiple or single tests. So base wall assembly, stud cavity installation, the gyp sheathing. A lot of people are starting to put wood sheathing in there, type 3 construction, FRTW sheathing, and studs. Originally, the test only looked at steel studs, but now we're testing wood studs in this test. Water-resistant barriers, the insulation and whatnot, because everything burns a little different. So if I were to look at a drawing that was sent to me, I'm going to look at it layer by layer. I'm going to go from inside to outside, and I'm going to look at that proposed construction. Obviously, the photograph here on the left, or detail on the left, doesn't have the base wall construction, but I start with the interior gyp. Does it have interior gyp? Does it not? Because I got to go back to a tested assembly and do a side-by-side comparison. So I'm looking at dimensions, air gaps, thicknesses of the insulation. Is the insulation the same? Are we having similar attachment systems? Is the veneer similar enough to what I have from a tested perspective? And I do a side-by-side comparison. If I have a tested assembly that I can use as the basis and the technical justification for any changes, then we end up writing an engineering judgment, stamp it, and get it out. But when I review things, there are a certain couple of buzzwords that I see on architectural drawings all the time, and I go back to our other fire and building life safety consultants, and I'm like, okay, you asked me to look at this exterior wall. What's rigid insulation mean? Can you go back to the architect and see what it means? Is it EPS? Is it XPS? Is it a polyiso? Is it a mineral fiber? Because all that changes where my brain goes in terms of an analysis. I know that EPS and XPS, foam plastic insulation, melt, drip, flow, and ooze when it burns. Where a polyiso, on the other hand, it kind of sits there and chars. It kind of holds its form and chars in place. And then mineral wool, we all know, is more on that non-combustible side and doesn't propagate flaming. Stud cavity insulation. Well, it just says bat insulation. Okay, is it going to be mineral wool bat or fiberglass, or it just says stud cavity insulation? Well, you can use spray foam in stud cavities and exterior walls. It's been tested. It meets NFPA 285. It meets those fire testing requirements. If you put up your thermal barrier per chapter 26, you're checking all the boxes. You can use it. But when I just see stud cavity insulation, once again, my brain's like, okay, do I need to go to the spray foam guys and look at the spray foam manufacturer fire tests? Or do I need to go over to the veneer manufacturer because this particular one is an MCM and they tested it with nothing in the stud cavity and they want to add in mineral wool? All things that I evaluate and where I have to go, because the testing is mainly held by the manufacturers. And then it comes down to foam plastics industry has a lot of them. The veneer manufacturers have a lot of them. The water-resistant barrier manufacturers have a lot of them. So it all depends on where we can find this information. A big popular one is I'm just going to throw up an AVB or WRB on the drawing. There's three main types: the fluid applieds, the peel and sticks, and the sheet goods. Well, they all also burn differently, and they also have different levels of heat release and total heat that can burn. So that drives my analysis as well. So if you have any of these materials, then I know depending on when you send out your drawings for review or third-party look-throughs, you haven't figured it out yet. You're still in the spec. The spec is still saying, well, here's your list of options. Well, just keep in the back of your mind that that spec, what you select, you need to go back to your exterior wall designs and make sure that the items in your spec can be used together. Because if I want to use an ACM panel with an XPS or EPS foam plastic, I can tell you right now, it ain't going to pass NFPA 285. So things to consider when you're looking at your specs. If you know early on, hey, I want to use an ACM panel, I want to use an EIFS system, I want to use an HPL, or I want to use one of the newer honeycomb panels, where it's metal, honeycomb, a bunch of adhesive, and a stone veneer. That new honeycomb product is in the 2024 code and required to meet NFPA 285. Reach out to the manufacturers of those products that you know you're going to go with. See if you can just get some basic information of their compliant assembly to start with, so you know where your guardrails are. EIFS, there's a lot of systems out there, a lot of different manufacturers. Some have up to 13 inches of foam plastic in their exterior wall assembly that they've tested for compliance. Some are only down to 3 or 4 inches. Exterior sheathing, I got into this a little bit. Is it wood sheathing? Is it Type X gypsum wallboard? Is it 1/2 inch? Is it 5/8? Because I got to go, once again, back to the test to make sure it's fully protected. Because that exterior wall, I'm exposing to a fire from the inside, the outside, and the header and jamb. So fire will find its way into that assembly, and I need to make sure that I'm getting it protected. So the takeaways here from today's presentation is that exterior wall fire performance, it does rely on larger scale tests. You're not doing a lot of small scale little Bunsen burners, or you're not doing combustibility ASTM E136 testing to prove these materials work in combination. You're doing a larger scale test with this because it is an assembly evaluation, and changing one small component like a water resistive barrier that's full wall coverage from a thin polyolefin sheet good to a really thick, goopy spray-on can have dramatic impact on the overall flame propagation behind your veneer. So changing that single component can result in non-compliance, and that could be flagged by third-party review, code official. They're really cracking down on, well, demonstrate 285 compliance for me, please. The generic terminology, I understand in the very beginning it makes sense, but as you're getting closer and closer to getting those specs finalized and submittals through, make sure you're going back and finalizing to make sure you know what you're using in a compliant situation. And that kind of rounds me out. I will be in the lunch area if anyone has any questions. So thank you all for attending today, and hopefully this was informational to you and the size and scale of fire testing and the world that I get to live in with Chapter 7, 14, and 26. So thank you very much.
Next up, we've got Dean White. He's Regional Facade Sales Manager at Cosentino, and he'll be talking about design with ultra-compact stone.
Thank you. Can you hear me fine? Is the mic working fine?
Right.
Good. So we're going to move pretty quick through here. We're going to talk about ultra-compact stone. This is also material that's referred to as sintered stone, sintered compact surface, ultra-compact surface. There's a bunch of different terms for this, but this is a material that's formed under very high pressure and heat. In layman's terms, you can kind of think of it as a porcelain on steroids, okay? Let's see if we can advance. There we go. So we're going to, sorry, it's not up on the screen yet. Thank you. I'm going to give you a quick introduction to Cosentino. We're a Spanish manufacturer in the south of Spain. We manufacture only hard surface products, including natural stones, that we are the third largest exporter in the world of natural stone. We developed quartz countertops back in the 80s, brought into the 90s. That's our Silestone brand. But for exteriors and interiors, anywhere there's a hard surface, we have our product Dectin, and it is an ultra-compact stone. All right, we are a sustainable manufacturer, so we are very focused on producing materials in a sustainable way. And in fact, Decton is the only material in its category that's carbon neutral. So I'm going to blow through this very quickly, but if you look at the physical side, that means we view the economy as a circular economy now, not back in the day when you would make a product, push it out one direction, transactional type manufacturing and selling and so forth. Maybe it was recyclable, maybe it wasn't. So we purchase from sustainable vendors for our raw materials. We design our products from the start to be sustainable. So we look at embodied carbon, recycled content, all these different things, that energy usage, et cetera, to manufacture. We design it from the beginning. We used best available technologies for production. I'll give you an example of that. Production of ultra-compact stone is energy intensive. Our emissions mostly come from the ovens. The last 200 meters in a production line, the material goes through an oven, gets heated up to about 2,300 degrees Fahrenheit to a liquid state, and then when it cools, it gives it pretty unique properties. We run those off natural gas right now, but we're switching over to biomass and hydrocarbon to bring down, or hydrogen fuels, to bring down that those emissions, all right? Energy efficiency, the entire campus runs only on renewable electricity. So we have largest self-consuming solar farm in Europe, which we're adding to, provides us about 25% of the electricity we use, and we use the equivalent to 400,000 homes worth of electricity at that facility. We also use a lot of water, and I like seeing some from my generation in here, so you'll know when I say we manufacture about an hour and a half from where they used to film all those Clint Eastwood spaghetti westerns, all those dry scenes, dry riverbeds, dry creek beds. Water is a real precious commodity. We recycle 99% of it that we use in the production process, and it's really key that we do that. We even built a treatment plant to recycle the water from the communities around it because it just evaporates if it discharges. Very important. We use it as a mixer and a carrier for us. Zero waste mentality in the plant. So everything we bring in the raw material side, we want to turn into some kind of finished good. So that often means secondary goods like road surfacing and so forth. And we reintroduce a lot of product recycled back into new material as well. Emissions, we use robot sleds and electrified processes to move things around the facility, conveyor belts, robot sleds, because the robot sleds go from point A to point B very efficiently, not like myself when I'm on a forklift and I have to zigzag all day long because I have my buddy that's standing 25 feet to the right and I gotta ask him how he's doing that day. No friends, right? A to B. Logistics, we're in 120 different countries. At any given time, we've probably got $100 million of inventory moving on boats and trains across the globe. So it's very important that we do that efficiently and we work with partners who do that efficiently. The product life cycle of Decton is 60 years, so it's a long life cycle, low maintenance cost, and it is recyclable at the end of life. These materials in this class, you mine 20 plus different minerals that have gone through the metamorphic process. You break them down, you reconstitute them in new recipes, and you put them back through the metamorphic process in a matter of hours instead of millions of years. So the important thing to know about these materials is they're slab materials, they're not extruded. So it's a dead flat product from a design aspect. You got to work in flat planes. Very dense, very consistent product. Same gauge all the way across the slab, same density all the way through. And then you have a product that has very unique properties. So it's UV stable. To the human eye, you won't see any difference in the color 40 years down the road. It's very non-porous, which means that if you get graffiti on it, you can just wash it off with soap and water. It's not a treatment. Okay, you can use a pressure washer. You could use harsh chemicals you want because these materials are very resistant to harsh chemicals. You can use them in labs and so forth, and probably the best countertop material you can use for that. Non-combustible. So we've got testing for all over North America, Canada, and the U.S. on combustibility, NFPA 285 testing, and Miami-Dade NOA testing for different systems. Graffiti and stain proof, like I said, low coefficient of thermal expansion. So you can get down to an 1/8 inch of a gap between your panels. It's going to depend on the building, of course. Large formats we'll look at real quick. Very consistent material. So unlike a porcelain that's thicker in the middle, thinner on the edges, denser on the surface, a bit softer in the body, these are the same gauge all the way across and the same density all the way through. Easy to maintain and clean, carbon neutral, and 25-year material and finish warranty. When you look at the formats, when you're dealing with these type of materials, you have to understand the formats they come in, because every manufacturer produces in slightly different size slabs, and that's where you're going to start fabricating panels from. So in our case, we have a couple standard sizes, 56 by 126, 64 by 130. When we added the 64, that was big for unitized construction, obviously, which was very important. It's relatively lightweight. So you've got 4, 8, 12, and 20 millimeter products. There's other products in the industry that are 6 or 5 plus or 3, but it is relatively lightweight compared to natural stones and terracottas, for instance. So you're looking from 2 pounds per square foot to about 10.8 pounds per square foot. Lots of colors, lots of natural colors, lots of opportunity for custom colors for minimum quantities. We do a complete custom for 30,000 square feet or less. Each manufacturer has a different threshold for that. That's probably the least. Most are started around 40,000. Some are still at 100,000 square feet. Ventilated range screens, unitized window wall, curtain wall, modular wall, and old-fashioned directed here. So there's a lot of ways to get on the wall. And really, you just have to think about the first thing is, do I want concealed attachment or visible? Then you can go down different paths for mechanical attachment, chemical attachment, structural adhesives, clips, rivets, screws, kerf, etc. So what this is just illustrating that there's different budget points that can get hit based on what kind of attachment method you got. Obviously, there's different performance that gets hit with that as well, but you can meet pretty much any condition with this type of material, because it can be installed in many different ways. Curtain wall, window wall integration, you can put it in a captured system or SSG. You can unitize it. When I look at, this might not come as a surprise, typically I see window wall gravitate towards 8 millimeter thickness, curtain wall towards 12 millimeter half-inch thickness. Probably 70%, 75% are undercut anchor mechanical attachment, not straight SSG. Even if they do SSG, normally there's some kind of, might be a mechanical backup or a lip that's helping with the dead load, etc. But it's very easy to work with from a glazing aspect. You use the same suction cups you use with glass. In fact, the material is quite similar to glass. Manufacturer will provide full slabs and have partners that do all the fabrication, or they'll provide cut to size with no holes or grooves, say it's getting glazed in, or cut to size with holes and grooves put in based on the shop drawings and the engineering that was done. When it's a ventilated rain screen or a curtain wall, window wall, it always comes with a fiberglass mesh on the back. That fiberglass mesh is for safety. So if it gets hit at height, you don't have shards falling down on people's heads. So here's an example of a unitized curtain wall that was done with undercut anchors, Kyle anchors, Cap West in Germany. So if you ever go to the BAU show, you'll probably see this building. You can see that it's unitized, it's a curtain wall. We provided it with the clips on the back that the curtain wall company provided us, because they just wanted to take it and plug it and play and hang it off their units. This is another case study we have in the Toha building. It's a pretty unique building because it's flipped on its head. The top is a restaurant, offices, and then down below where you see that solid beige area, that's actually the mechanical area. And in that area, they brought the panels together in an X-shaped pattern to provide ventilation to that area. This was done with undercut anchors. Here you can see it closer. The slab edges were wrapped as well. And that is the baby in the front on the left there and on the right. That's the smaller building, and now we're doing the 75-story one next to it. The smaller one was done with half-inch with undercut anchors. The taller one's being done with honeycomb with 4 millimeter dectin on it. So there's a lot of different ways to skin the cat when it comes to using these materials that'll hit different budget points, different designs. And this type of material is a type of material you can use anywhere there's a hard surface, interior, exterior. So when you're designing, you can have that flow from interior to exterior. You can tie different elements together. If you're going from a rain screen up into a window wall or a curtain wall in the tower, you might be down on the podium with rain screens. You can carry the same material through, or the same pallets, etc. Okay? Please stop by and see us at the table, and we'd love to give you more information on it. All right? Thank you so much for showing up.
Next up, Natasha Appel. She's a business development manager for EJOT, and she's going to be talking about rain screen attachment, stainless steel.
Good Good morning, everyone. Thank you for joining us. As previously mentioned, I work for EJOT. We are partner in a lot of different panels optimization. Today, we're going to talk a little bit about our company itself, but we're also going to talk about what makes the stainless steel the most sustainable material and the most economical choice in a lot of cases. As you guys probably know, ventilated facade come in a lot of different choices. When you have a choice between subframe and component, they range from aluminum, stainless steel, there's a lot of other materials, some of the newcomers, there's a lot of different ways and attachment. The difference between them and EJOT is we are a family-owned business all over the world. We have over 100 different locations. We have a lot of patterns. We invent a lot of our screws. We're supplying everything from the bracket itself to all the screws. And ventilated facades is probably one of those things that everybody from architects, engineers, installers, all agree on one thing. Somebody else is responsible for subframing, right? And when it comes to ventilated facade, that's also another thing. So we always spend a lot of time on selecting the panels. We select the looks, we select the size, we select the style. And most people assume that subframing is something that's interchangeable. It is not as easy as that sounds. The substructure is responsible for a lot of things. It has to be flexible, but it also has to be rigid. The system on a wall is responsible for the dead weight, wind loads, movement of the joints, movement of the substrate, movement of the panels, expansion contractions of the actual structure. So it becomes a very important piece when we design in the building, because again, two presentations ago, you guys seen a lot about fires, and non-combustibility is probably one of the biggest elements that comes to ventilated facades. But also, subframing is typically on the back of the panels. So when it comes to the back panels, it's very hard to constantly review what's going on there. So you want to make sure that the elements you're using are very high corrosive elements. They can withstand salt in the air, they can withstand moisture in the air, and they are not going to fail because they're going to fail slow. By the time you typically notice any visual signs, it is already too late. So one of the biggest things for us to consider is obviously how those panels are attached, but also how are they moving. And the most important elements, as I mentioned earlier, are the elements that we don't see. All the screws, all the anchors, all the attachment systems. Because one of the biggest things, if your facade going to fail, one thing that's going to fail is the screw. First screw that attaches the bracket to the wall is typically the smallest element that most people don't even pay attention. But the rest of the system have to have resistance to fire. It has to be structurally sound, but it also have to move. And it also have to have a thermal performances. And this is one of the biggest elements that stainless steel can bring. It needs to be a corrosion resistant, and sustainability is actually coming more and more in everybody's lives. So one of the biggest things when we talk about fire is fire lets you know when you screwed up very quickly and very expensively, right? We always design facades, but we need to look at it as designing the system. We're designing performance, not elements. It's not just a detail that you're designing, it's a performance that you're designing. So how do we protect against fires and catastrophes like that? Building codes, which we covered very detailedly earlier, cavity barriers, using non-combustible material, and using subframing that essentially going to keep all of those materials on the wall without falling down, without crushing down, without spreading the fire. And we want to make sure that the system we're using is not going to contribute to the failure. When you compare traditional stainless steel to traditional aluminum, just the generic run-of-the-mill parts, you will notice that stainless steel has 2 times higher melting point. I know we have here in Celsius and in Fahrenheit. If you compare traditional aluminum, it's typically 1200 degrees Fahrenheit melting point. In the brackets, we also use polyiso thermal break, which also does not burn. Stainless steel melts at 2600 degrees Fahrenheit. So one of the biggest things what this number tells you is that it's not just the melting point for the material, it's the amount of time now you added that you can safely evacuate people from the building. It's not just, again, comparison of how the material melts, because material is not going to fail just after it melted. It's going to start failing as it heats up. So having material that have a higher melting point allows us to create the structural pieces that are going to withstand longer temperatures for longer times on a building. If we're talking about thermal performance, one of the biggest things you notice that stainless steel has 15 times less thermal transfer than aluminum, which again kind of makes a lot of sense. And if you actually look at the thermal images, you can see tiny little points where your thermal transfer happens in the aluminum. It doesn't look significant, does it? But imagine you have tens of thousands of those points on your building. They suddenly become not just a tiny little holes on the building, they become highways where all of your energy goes to. That also takes all of your money on that highway. The next point is also very important because we live in a real world, right? We have oceans, we have pollution, we have a lot of different conditions, salt in the coastal environments. So it's very important to have material that can withstand all of those elements. Permanent exposure to any of those moisture can weaken the smallest parts. What are the smallest parts? The first things that you fail: anchors, screws, connectors. They are very hard to assess if they are failing. So a lot of times we want to make sure that something as insignificant as anchor is properly selected, properly sized for the substrate system you're using. Stainless steel, as you guys know, has a life expectancy and been used in architecture for many years. It has typical life expectancy of 100 plus years. And it's very corrosion resistant. It has a lot of different options for uses from the screws and anchors. We also have two different alloys that we can produce. One alloy specifically for the coastal environments or when we have a very high chemical imbalances in the air. And it's a very low maintenance as well. We have two different alloys, as you can see there. There's 304 and 316. 316 is typically recommended for the harsher environments like the coastal applications. Recently, you probably guys noticed that sustainability is no longer an option. Sustainability is something that we all have to deal with on a daily basis, even if you don't use the word sustainability. 39% of emissions come from the construction industry. That is a lot. So when we're talking about sustainability specifically, we always talk about recyclable material or recyclability or percent of recycled in the material itself. Stainless steel is one of those materials that can always be recycled, 100%. It's also is very easy material to recoup. When we melt aluminum, we can lose anywhere from 20 to 40% of its mass. When we melt stainless steel, we always can recoup at the minimum 98% of the material itself. But one thing of sustainability that most people don't talk about or we don't think about this, it's not how well a sustainable material itself, but how long this material can be used. If we have a material that can be used without replacing, without any special needs for it, for many, many years, it is a lot more sustainable than any material that you have to replace every 20 years, 5 years, 6 years. So the goal is to include the material that is not just sustainable in its nature, but the material that is has a very long life as well. The benefits of stainless steel, again, kind of comes from the actual material itself, because it's a very high recycled content. It could be as big as 60%. It could be, in a lot of cases, more than 60%. We use it in almost every part of the building, and it's always salvageable. If you have a building that's through demolition, all of that steel can be reused somewhere else. It has a very high scrap value, which means that we can keep that material from the landfill because it's simply too expensive to throw away, so people tend to recycle this more than any other material. It has a very low lifespan, and it also has a very long service lifespan as well, which is, again, very important for a lot of us. So when we talk about sustainability, we talk about the material performances. One of the biggest things is we need to consider the subframing not just as an add-on, because this is essentially what's going to keep your panels on a building. It is the system that is a lot more important than the visual look of it. It is going to either fail the building or if it's going to stay on the building. We are at the table in the lobby. Please stop, have questions, I'll be happy to answer. Thank you guys so much.
Okay, so next we'll welcome Deniz Arslan, Senior Computational Designer with HKS Line, and Tim Logan, Regional Practice Director, HKS Line. And they'll be talking about differentiated deployment of modular GRC panel systems, that's a mouthful, and a case study. So thanks. The clicker is right there.
Okay. Nope. Yeah, thanks for having us, everyone. Differentiated deployments of modular GRC panel systems. We're going to talk a bit about our work process, I guess, when we deal with facade design and execution, I guess, within the context of the arena at Diriyah Gate, which was recently completed in design, but is still not yet constructed, so still pretty fresh in our minds. Yeah, Tim Logan, Regional Practice Director in Central Americas with the Laboratory for Intensive Exploration, as we call it, or LINE for short, because Laboratory for Intensive Exploration is also a mouthful within HKS.
It's Deniz Arslan here, and I focus on data-driven development. You will see what that means in a second.
Yeah, so just a little bit about us. HKS is a company that's been around for a while. I think we're in our 9th decade or pretty well into the 9th decade of our existence. And then LINE as a group has been around for about 10 to 15 years. Our focus is still as a design studio, so we focus on trying to execute designs, but as part of our charter with HKS, we get a little bit of overhead time to spend on explorations. So oftentimes that's project scale explorations, not usually like long multi-year ones. But we try to use that time to produce better designs and to help out other teams within the company as well, which is kind of how we tagged into this one. We do have a lot of history with sports projects in our team and within the firm. We did a lot of big NFL stadiums over the years, starting around the time I started at HKS with Indianapolis and AT&T in Dallas, and then US Bank in Minnesota, the first big one that I worked on, and SoFi, which we recently finished in LA. And then, we're still not stopping there. We've got the Cleveland Browns that we're designing currently that's underway. That'll be done in a few years, hopefully. And then just recently we were announced as the design architects for the new Washington Commanders Stadium. There's not a whole lot I can say about this one yet. It's still really early in the design phase, but we figured we'd bring some images to show you anyways, just because it's fun and it's DC. But hopefully, soon here we'll be able to talk more about it and maybe come back and present on this project in particular. Our studio tends to be thought of as kind of a computational design studio too. Computational design is often thought about as a series of tools that you use for the process, but it's really about how we think about and break down problems within the design work we do. So, using computational thinking as a problem-solving framework and not so much as thinking about which components we're going to put on the canvas. And oftentimes it sort of starts to coalesce around a few major themes. Data-driven design is a big one, whether it's, client-driven data or contextual data, bringing in simulation and analysis to drive things, getting into digital fabrication, or maybe more aptly put, how we communicate with fabricators and builders to execute our design intent. And then parametric modeling is kind of the thing that brings it all together. Which brings us to the Diriyah Arena. Here shown with the triangulated facade, which was designed for it, which we helped to execute over the last couple years. A little context about the Diriyah Gate region. It's in sort of northwestern Riyadh in Saudi Arabia, which is kind of centrally located in the Najd region. There's a lot of architectural vernacular around there, around sandstone, with a lot of triangular openings and geometric patterning that we tried to carry across into what we were doing. So that was a big influence on the overall design. And then sort of how it would sit within the context of that region, similar sort of material palette, trying to show a similar monolithic look to the design so that it showcases itself while still fitting into the overall region. And then the design for it itself was expressed as these sort of massings that grew out of the ground that we started calling monoliths. It gave us the ability to sort of play with scale a little bit and have smaller ones that are a little bit more intimate as you enter the building, and then larger cuts and different maneuvers happening to create terraces or skylights to bring the whole building together. The design itself is centered around this multi-purpose flexible arena. It seats about 20,000 people, so it's a decent-sized arena. And we tried to bring some of the same design aesthetic with the monoliths to the interior as well. So there's, you can see on the left-hand side of the image some thinner monoliths on the interior as well that have the same kind of expression and will use the same material palette. And then just sort of another look of what it looks like and how it fits in with the local stone. All rendering still because construction hasn't completed yet. But then a little bit more about how the pattern starts to appear on the building. So the triangulated pattern showed up really early on because of trying to fit within the aesthetic of the Najdi region and vernacular. But they wanted it to feel more textured and rough at the base and then start to smooth out as it reaches towards the top of the building. So there was a sort of typical gradation that would happen. And then that's about the time that they brought us in to start talking about how we would handle the facade. At this stage, the design team that was based in London for this project had treated it as kind of a mass customized facade. Every single panel was similar, but probably a little bit different. They weren't really trying to bracket any panels into a minimum number of types. There was probably some expectation around some of our other projects that had some mass customized facades. But it doesn't really fit within a cast system like GRC. So we came on board to start looking at evaluating the facade to try to simplify it while still being able to pull off the design as intended. Then I'll hand off to Deniz.
Thank you. How do you make a facade like this happen? Some of the parts is starting with the data structure itself. You might think of it from macro to micro, radially clockwise, starting from the exterior monoliths, then it's going into the faces. So what happens in the design phases? We have SD at first, and IFC and designers tend to change the massing a lot. You have to remap this structure and create safeguards to adapt to what was it previously done as. So the lighting designer places the LED on this monolith, let's say. It moved 5 feet and there's another face added. We will adapt to the nearest structure with a script. In addition, we have the row numbers and panel numbers here. This way, we have an ID for every single panel that goes into Revit. You can identify it when you're building it, when you're rotating it. It's always there. What type of panels we have is we start with a base rationalized triangle. Then we have the extrusions varying in size and depth. We also have LED panels and punched openings. Next, we have the textures that we will get into. This is a whole different ballgame. But if you see in here, there's full panels and trim panels. The full panels can be optimized, and trim panels is custom panels that we will have to minimize the number of. So we apply something like an evolutionary algorithm. This way we can play around with the horizontal system and get the least number of elements. Or we can have scripts to have the most visible corner of the seam aligned perfectly. How do we get that organic, local feeling look that's not repetitive to the eye? There is multiple dimensions to control this chaos. So there is the vertical panel grading, edge grading combined together. Then we have the randomization factor here to have that natural look. And in addition, we have the rotations that we have limited. This is the script that outputs the ID that goes into the Revit. Take over.
Sure. So on the Revit side, there's always a bit of navigation that has to happen as we sort of translate from a CAD-based or design-based model to something that's going into our documentation model, and typically that's going to be a BIM model, even though I know model's redundant there in BIM, but I can't help but saying it. So every project we tackle this problem a little bit differently. This one was made a little bit easier because it was in the contract that we had to have a fully native BIM model. So there's no playing around with making decisions about what needs to go in or what can be imported CAD or something along those lines. It all had to be native. So that sort of developed our strategy around it. So we developed two different work streams, one for the sort of typical equilateral triangles that fill up the main part of the face, and then another for the edge panels. Both tracked along pretty similarly, but for the field of typical panels, there was I think 12 or I guess 8 different types of components that were made for it that were parametric, that could scale, because each different face is a slightly different size triangle to make up so that the horizontals track across properly. So those were built, and then as they were picked out from the previous exercise and how it was designed, we would then populate that and just instantiate it in the building. And as part of that, certainly tracking and pushing all of the metadata that we were designing along the way gets pushed into the panel objects too. The trim panels were another interesting one. Those we used an adaptive component system because there was just too much variation to deal with. As we evaluated the design, it's pretty easy to come up with how many vertices are happening in any of the trim panels. The vast majority were 3 to 8 points. There were a handful that had even more than that we handled separately just because it wasn't worth taking the time to develop, a bunch of little one-off systems for things that were a much smaller quantity. There's also practical reasons why this is separated out from the full panels, aside from the different sets of types that were being used. It just takes a lot longer to produce these inside of the BIM model. I think it took an hour to an hour and a half, depending on which computer was used to produce these. Whereas all the main triangles in the face took about 5 minutes to populate across the model. So if we're having to deal with like modifications around it, and most of the changes are happening around the panel design, it's a lot easier to just kind of push updates to those panels than it is to try to produce the entire thing. But we're still pushing the same metadata. Everything's coming across and being stored as parametric data within the components as they're instantiated. And then, we're able to quantify things and understand them a little bit easier. Every single monolith that was documented, we produced a little axon shot that would show the different faces so we could label them. You can see an example of what the parametric model looked like for the individual components. Lots of little reference lines and planes to develop them. But it let us quantify them so we could have schedules for every single face. We could have we could tag it anywhere within that face and be able to tag which face or which monolith it was part of. So it was a lot easier for the documentation team to take it and run with it with that. And then, it also allowed us, all the work that went into the upfront part allowed us to be able to change things easily. So if the panel design needs to change, we could update that pretty easily without, having to affect the entire model. If we had localized modifications we wanted to do, maybe an entryway shifted a little bit, we could just target and change those specific ones because as Deniz said, everyone had its own custom unique ID, so we could track it and reproduce it as needed if something changed with it. And this is just, we've been working a lot on workflow for these kinds of automated processes. This is kind of a diagram of the old school way that we did it, probably before our team formed. And there's teams still that are working on it in this way where it's a very explicit modeling exercise. Oftentimes there's a design model and a documentation model that are like running parallel for probably way too long, that are never quite in sync. So it's something we've constantly been trying to get around. As we start getting into the more computational design workflows, we're the ones that are producing part of the documentation model. So we have a lot more control over how we're pushing that information through and being able to iterate a lot more within the phase that we're doing, because we're not spending as much time explicitly modeling and remodeling everything, even though it is effectively being remodeled. It's just a lot more automated. That also allows us pretty easily to see comparisons between like a price documentation model and square footages for the different systems we're designing for the facade, compared to what we have in current iterations or design alternates within the design model. It lets us hit our targets a lot easier when we can sort of know and quantify the pieces a lot easier. And also you can start quantifying the different design items. This is, example from, it looks like the Brown Stadium, where we're targeting and looking at different sort of panels along the way, so we understand what we've got. And if there's some types that have higher yield problems or fabrication constraints around them, like we can minimize and understand around that too. And then I'll let Deniz talk more about some additional workflow.
So in SoFi or the GGA project, the computational designer has a scope. It can be just the enclosure, for example. We are helping integrating to the system, creating a bunch of alternates. But we are not a full organism like we are in the later processes. In here, the designers saw that what we can do and how we can even improve stuff like documentation. Every time you will change a tag, for example, you're changing the entire building, you will have to redo that type of work. But our team works differently, and we will always set up a pipeline to automate that process. So we have alternates, and we have past documentation. So this is what the workflow looks like right now. The darker blue is the system. Let's say we are designing the roof, the colonnade, the glazing system, all together in here. Let's start with the structural frame. This can have so many varied choices. So each time we have a wireframe, let's say 4 options, we can send that to the structural coordination in start and get the exact number of pricing of the elements, or how will that impact, or we can do simulations to relax the roof cable structure to have a more informed design. This process also generates a Revit model, which is informed by the BOW structure and the documentation team, working as a full architectural team model. But not just that, we have things like energy models that can come out in an idealized scenario, or the facade detail model. You will like to do a thermal analysis, and that will mean you need really scale of the grazing there. This can generate different scales of the same thing. Or it's always create tabulations. When you have 30 alternates, you need to get the deltas of how many elements you're getting for each one. This automatically saves it to archive. This compares numbers, and then you get to the design review board. This process generates its own data while also being informed by the data we get from the consultants. This is one of the simulation examples. Daylight, for example, a simple one. But it's so much more than that. Think about a timber building, for example. You have glue limbs that is a connection of lamellas. If you combine the lamellas vertically or in different thicknesses, you can create different curvature in that building. That will impact the design. Or you can analyze the snow gathering on a roof and design accordingly. We are not trying to move away from consultants, but we are trying to design in a more informed way to have these conversations. What happens when we get a new roof design, for example? We got a design input. Is some person going to design the roof and the next person going to update the glazing? No. We have a triggering system that will generate all of these products that I mentioned before, while being also informed by the slab edges that's been changed in the Revit. So let's say we have 30 alternates. If this is selected, we can send this to the engineers as a wireframe, as an option, really fast without the previous waiting time of the modeling, which makes most of the difference here. So in here we see how the goal and simulations are all connected, collaborative, a feedback loop that brings more to the design.
Yeah, and just really quickly, like this is the stage where we start getting into getting ready to test fabrication processes and building out things. And it's always a really important stage for us as we go from the digital to the physical space. There's a lot of learning that you get when you actually see something made and see how light affects it and you know how you experience it. So typically we'll cast a pretty wide net and try to find a lot of partners who are willing to do, you know, at least walk through the process with us and talk about how they would tackle a process. You know, GRC manufacturers in this case, but it could be a metal fabricator if it's on a metal facade or you know, a precaster. Really anyone that we're targeting, we try to get as many opinions on how to do it as possible so that we know what we can do with the system and it lets us take it to the next level.
As you said, we do a lot of collaboration. We do R&Ds and reach out to a lot of different manufacturers to understand the constraints of these materials. So, what happened in Drygate maybe is that we might not have liked the first mock-up. This is a typical thing that happens. So we want to improve the texture, so we apply the same systematic data-driven technique to textures. In here you see a BPR texture applied. This has different normals applied to it, bump maps applied to it to create this density at different scales. You see different panel types are defined by these systems. And these are the different bump maps that I have created and sent it to some of the consultants we might have. This is our work with spacecraft. As an example, we discussed different ways of creating this. So we went with the first one for the initial option, the digital texturing. Here you see the digital delivery of texture applications or how you made the mold. In different processes, we go into details of how many times you can use the mold to reduce pricing, or even things like curing. In some of the projects we worked on, we did curing application by time and G-code to idealize the process flow and the drawings on the panels. This is what we got after the acid wash, and here is a close-up. And we want to get as close to the organic feeling that the client requested as we can. That means a lot of design reviews. Now we are informed by the fabrication concerns. Next we move on to panels. There's 12 panels. There used to be a different number, it's updated. And how can we play around with this? This has multiple artificial joints, the primary one, the secondary one. I have created a script to change the widths and the depths and the incline angles, and the textures apply to that panel. Why do we do that? Like, when it's an individual material, it doesn't matter. But when it's applied in mass scale, you see that creates shadow lines, even though it's not repetitive when it's always facing upwards when you're looking at it. But when you repeat it, you can see, even though it's not actually repetitive in the gradient, the shadow lines in 3PM makes it look like it is. Or you get stuff like here, it can become a hexagonal star-like feeling. And we want to avoid that. So these are the implications of those small changes in the full mass scale. Here we see an improved version. What has changed? Things like removing secondary joints next to the smaller triangles, or adding wider and deeper primary joints, adding inclined instead of extruded secondary triangles have been updated. And these had a huge impact on the design itself. We also added things like straight cut angles to the sides and to the inclines to have that more realistic cut stone impact that we were hoping for. This is just a small example of what we did in this process. This was GFRC, but we also looked at GFRP and what happens when you combine both of them. For example, over time, with the weather, the coloring changes fully. How does the structure carry these separately? These are all of the things we kind of look at and sometimes go so much more in depth to.
Yeah, there's a lot that every time we take on one of these projects, we always try to learn as much as we can, again, about the different material systems and really think about what the life cycle of all of it's going to be. And really try to build partnerships with the fabricators who are making things. It becomes really important to build trust with everyone that's part of the process. If you try to push a little bit harder than some of them are comfortable with, it's good that they're friendly with you and you're friendly with them. So there's a lot of relationship building and a lot of trying to work with and pull the best out of ourselves and pull the best out of the fabricators that we're working with on all these projects. And I think that was it. So thank you for your time. I hope you enjoyed the presentation of the arena. And yeah, look forward to hearing more from everyone else.
Thank you.
All right, so we're going to move into our first panel discussion, and there'll be a little bit of housekeeping here while the chairs are set up. I'm curious for the I also did want to say I appreciate that they're not trying to get rid of consultants. As a consultant, I appreciated that. But how many in the room, how many of you is this their first Zak Façades? Okay. How about architects in the room? Engineers? Okay. Manufacturers? Nice. Yeah, it's a good mix. I was excited when they came to DC for the first time a few years ago and to come again. For this panel coming up, the moderator will be Matt O'Malley. He's a pre-con and commercial market lead for DPR, and he will introduce the panelists when they come up. But they're going to be talking about biotech facilities and understanding how the facades of those facilities can create a healthy internal environment, which I think is really interesting.
You're first, right? Yeah. All right. Thank you, everyone. Glad to be with you here today. My name is Matt O'Malley. I work for DPR Construction, do pre-construction. I've been a general contractor really my entire career. I did go to architecture school. I sold out immediately and went into construction, which is the advice that I give young architects in school. Sorry. But I, throughout my career, I've had the opportunity from the general contractor's perspective to be involved in the exterior envelope through some different roles that I've had in my previous company and my current company, really to be engaged in, the delivery of high-performing facades. And so it's not necessarily my day-to-day job like I think it is for some of the other folks on the panel, but I guess I'm probably stealing this term from somebody that I heard years ago, but I'm more of a facade enthusiast, I guess, at this point. But I'm happy to be here and talk with this panel here. We're going to talk a little bit about laboratories and life science type facilities. This is something that I got involved in a few years ago, as here in the DC area, we thought there was going to be a big boom of life science development. I'm not sure that ever really actually happened, or it happened at a lot smaller scale than people assumed. But, I think for a lot of people who, like myself, probably have spent a lot of their career working on commercial type buildings, commercial office and that sort of stuff, there are some unique issues and challenges when you're delivering a building that maybe from the outside kind of looks like a commercial office building, but it operates very differently on the inside as a laboratory, research and development type facility. So we've got our panel here. I'm going to let each person kind of introduce themselves, and we have each panelist has a couple of slides. They're going to highlight a project or two, and then we're going to have some Q&A with myself and the panelists on some of these topics. Okay, John, you want to get started?
Yeah, thanks, Matt. I'm John Barbara from ZGF Architects here in DC, and talk a little bit today about the assembly. This is a project ZGF collaborated with Wexford Science and Technology and University of Pittsburgh on up in Pittsburgh, and really interesting project. Basically, it's the adaptive reuse and repurposing of a circa 1915 Ford assembly plant, which you see here. See if I can get the spotlight to work. But you've got the assembly plant, factory building, and then the adjacent crane shed. And it's an interesting story because there were 25 of these built around the United States at the turn of the century. And they all kind of worked the same way. You know, chassis and engines, motors were made in Detroit, put on a train, and other components and parts, and then sent to these assembly plants where they'd bring the parts in, lift them with a gantry crane and assemble them, and then sell them out of a showroom on the ground floor. You know, great project. Program entails about 233,000 square feet of renovated space, 163,000 feet of new space, and about 128,000 square feet of parking for 325 parking spaces. The team included ZGF, Thornton Tomasetti and A&F structural engineers, and then AEI did MEP. Turner Construction was the builder. Design started in 2018, completed in 2022. Project achieved LEED Gold, and obviously we saved a lot of embodied carbon by reusing the building. So look forward to speaking more about it.
Hi, everybody. Can you hear me okay? I'm Tyler Grimshaw. I'm with Ewing Cole Architects, and I'm out of our Baltimore office. We've got a number of offices up and down the East Coast and also on the West Coast. Let's see if we can move forward to some of the slides that I'll be talking about today. Primarily, I'll be focusing on a few projects that we did between 2018 and 2025 for Alexandria Real Estate Equities. This is one at 9950. It is a cell manufacturing facility that AstraZeneca moved into. Does this go back? There we go. Sorry, I skipped one. This was another facility, 9808, just around the corner, currently occupied by multiple tenants, most notably some NIH activity that's going on in there. And then this is a campus that's known as the Alexandria Center at Treville Gateway. Miltenny is currently in there right now, and there's 3 buildings planned to be on this site with a 2-phase parking garage. And then lastly, just to represent sort of a diverse set of projects, this is something for Kite Pharma in Frederick, another big hub for biotech manufacturing in Maryland. This is for Regenx Bio, which is also in that similar area along Shady Grove. And then this is a BSL-3 laboratory that we did for the Maryland Department of Agriculture out in Salisbury. So we'll be going through a couple of those to talk about facades and sort of controlling pressurization related to lab facilities.
Hey everyone, so I'm Daniel Lucenti. So I got asked to be on this panel because I heard that not a lot of owner developers come to these events, so I kind of bring a little bit of a unique perspective. I'm actually an architect, so I'm kind of a sheep in wolf's clothing, in a sense. So my previous life, I worked at Iris St. Gross Architecture for quite a long time, and then before that, did some other in some other firms locally. So the funny thing about this project is that this is the Pearl in Charlotte, North Carolina, that we just finished up. I actually managed the master plan for Air St. Gross, then went into building design, and about 50% CDs transferred over to Wexford Science and Technology. one thing that I really liked about Wexford is that, we care about the buildings that we build. So not your typical developer, which is the bottom line, which a lot of projects kind of somewhat, go to. And so we really care about the facades, really care about attracting top clients, tenants. And so that's really kind of what drew me. So I'm mostly in the design and construction side. So I manage the design teams and the construction of the project for our portfolio in the Southeast. This project is, so it's 2 buildings with 2 parking garages and a whole site that was done in, about 5.5 years from master plan all the way through building completion. It's the Wake Forest University School of Medicine with HM Health, and Charlotte was the next largest city in the US without a 4-year medical school, which is what brought this here. The building to the left, which is the white kind of fin building, that's more of our typical research lab science type building. And as you can see, the facade's pretty interesting on that one. So kind of we really care about those facades. So kind of we'll use the following slide. I'm not going to really go through all the other slides, just because, if you want a little bit more, just give them a little taste. But there's some slides in here that we'll talk to you through some of the questions.
Okay, great. Yeah. All right, so maybe I'll start with John, if that's all right. So I'm curious about the adaptive reuse challenges and constraints that you had on that assembly project, and I've seen obviously some of these images before, so there's some really cool stuff he's got in here. But I talk a little bit about how those the constraints sort of impacted the facade strategy on the project, and then I guess also kind of maybe tie that in with like the life science program as well.
Thanks, Matt. Yeah, so just to kind of do a quick overview. So this, again, I already mentioned the project has the original assembly plant and the crane shed. These buildings, they're both barrier wall buildings. The Ford building was in good condition, repointed, recently restored, has some ornamental terracotta on it. The crane shed, the green building, was not. It was in very, very bad condition, and I'll advance here and you can kind of see. So, upper right, or I guess it's your upper right as well. Upper right is what we found in 2018. Lower right is what was there in, 1920, 1915, pick your date. But basically, the big constraints, and there were many, but I think, this project was made feasible by historic preservation tax credits. So it was listed on the National Register in 2018, and that enabled the financing to go forward to make this project happen. Very complicated project, which Wexford very skillfully managed. So we had to deal with the existing fenestration, the existing shell, and we had to get a fairly complicated program into this shell. Everything south of the red line is the new addition. Everything north of the red line is the existing factory and crane shed. So we really let the fenestration kind of speak to the program and inform us where the program needed to go in the building, because we had, and you're not seeing all the levels here. There's two more levels below grade in the original building and 4 more levels below grade on the addition, which are parking. But we had to, put the myriad of different spaces into this shell. And, we had high humidity areas. Most of these are, regular BSL2 labs, which, are negatively pressured. But there's often a lot of requirements in a life science building. As Tyler mentioned, pressurization, either negative or positive. Clean rooms are typically positively pressured. Dirty spaces, labs are often always negatively pressured, but those pressures differentiations can be huge. So knowing that and kind of understanding how we could take advantage of this shell and really capitalize on daylighting, because we really wanted to. This project, the heart of this project is the crane shed, the atrium, and it's a lot of space to build and condition. So we really wanted to make that the kind of the touch point, the identity of the project. So we basically we worked with the fabric. We had the MPS regulations We had to follow those. We had to do a lot of restoration to the project, but we really looked for opportunities to use the existing fenestration to create collaboration spaces, to create spaces where people could meet and exchange ideas. So really daylighting and collaboration were the big drivers and how we kind of laid these, laid the spaces out. And there were other constraints, floor to floor height, 13 feet with a 20-inch slab. So we kind of celebrated that and left all surfaces exposed. We also had constraints with structure and the penthouses. All the penthouses were modules that were brought in, 34 of them, about 50 feet by 14 feet, made in North Carolina, shipped up here, and we had to put a whole dunnage system on the roof. So there were a lot of things like that we had to adapt to. All the shafts in the existing building were heavily reinforced with K-braces, and I can share some images. I'll get into some of this in the next question, but if we look at the Ford building, you can see, a lot of structure. And so we look to take those constraints and play them up, to the advantage of the program and the building. And again, to really create a premier space for the researchers. And the other thing we did that's often done, going the wrong way. Very typical in a lab building, but we use the write-up spaces, the PI spaces around the perimeter, which are blue on a typical floor, to be a buffer to the envelope. Because the envelope is, it's fragile and it's 110 years old, and I'll get into how we dealt with that later, but we use that as a buffer, and the orange and the light orange is all the wet lab space, which is also, a containment area or an HEL. So there's a lot of requirements that have to go into one of these buildings, and to put it in a 110-year-old shell was quite interesting. So
you can hand it to Tyler probably. I'm going to ask Tyler one. So thank you, John. So one of the things, I think I mentioned this in the beginning, so when I got assigned to start looking at some of these life sciences buildings several years ago, having done a lot of commercial office, I don't think I really sort of appreciated some of the differences in the interior environment of the building and how it needs to perform and how that's different than like an office building. So things like daylighting, you talked about the pressurization, the mechanical constraints, different humidity levels, that sort of stuff. So I'd like to, Tyler, if you could talk a little bit about that, like how do those factors play into how you design the facade and some of those technical challenges?
Yeah, certainly. I think there's probably a number of products out there, that everybody's had a chance to look at, and you can see where things are evolving in terms of the envelope, and maybe, one different perspective that I could bring today is that very early on in the process, one of the things that's very important for some of these companies is understanding that by the time these facilities are complete, they're going to have an operation in place that needs to be validated. And so, more and more these days, what gets written into their validation protocols needs to be extremely well understood by the design team. Part of that validation process is how they monitor their space. So a laboratory or a manufacturing facility, they may monitor pressurization down to 0.05 differential between rooms. They may monitor relative humidity of their labs between a certain percentage, say 40% and 55% relative humidity. And the same goes with temperature. It could be anywhere in a range between 68 and 70 degrees. All of those numbers go into their validation protocols. And all of those numbers have to be maintained in order for their space to be validated. So understanding that up front is critical. And because the systems are moving from periodic monitoring where somebody may come in annually or quarterly to inspect the lab to make sure that it's up and validated. More and more we're seeing that it's a continual monitor that's taking place, and more we're seeing added data points for that. So not only is the monitoring on the environment itself, it's also on the equipment in the environment. And all of that, I guess, leads into, how does the building function? Different from maybe an office space or a school or, something that has, just people moving through the space. These buildings are more tightly controlled, right? And so you don't see a lot of windows that are operable in the lab space. Now, where we know that we're planning for office space and we're looking for lead credits and things like that, we're definitely trying to get as much of that into the design as possible. But for the core lab functions, we're really working with a fixed glass situation. And the fresh air that's being brought in, that's coming probably from a dedicated outdoor air system that's usually on the roof of a building about this size. That brings the air in, and that air gets conditioned. The humidity, especially in Maryland, I think, was it this last week where we had like a 40-degree drop in a single day and met a record? Imagine a HVAC system trying to handle that type of difference. So the building envelope really becomes more of the separation between the outside and the inside, less a part of the ventilation system. But that outside versus inside has to be moderated, right? Because you can have such extreme differences between the outside and inside that can impact the pressurization and the humidity and the vapor that is getting carried across that weather barrier. And so, what we look at as what's important relative to the envelope is number one, just the good practice that is the current industry standards, right? That's making sure that your vapor barrier is continuous, making sure that it's placed in the right place. In Maryland, that's, you always want to be on the warm side. And then having those studies that investigate how much insulation you need and where placing that insulation affects your dew point. So you never want your dew point to fall inside your vapor barrier. You also don't want to create more than one vapor barrier. And with lab buildings, you often have clean room liner panels on the inside. So if you have a space that is on the exterior of the building, you could potentially be, creating a sandwich where air could get trapped or moisture could get trapped. And so you have to be really careful about understanding where that dew point falls to make sure that it doesn't make its way into the building. Those are just a couple of things that, just come to mind relative to how the envelope functions. And then with daylighting, right, give you an example, back through here, the envelope becomes in an open lab situation like this one in the upper left corner. It becomes an opportunity to integrate some of the newer systems. This building, to ease up on the interior conditions, we fritted the glass. On the previous building here, we introduced some vertical louvers, and those were directly, the attachments for those were directly integrated into the curtain wall system. And it's obviously also an opportunity, like this building here at 9808, for just sort of decorative elements, lighting elements, and figuring out ways to integrate all of those systems together into a one common system as the envelope.
Great, thanks. So Tyler mentioned a bunch of these technical sort of numbers. I didn't understand any of those numbers that he was talking about at the beginning. But obviously those are very important to the tenants, right? So this question's for Daniel. So as a developer, real estate developer now, I think one of the things that I don't think I really appreciated either was that, a lot of these buildings don't have a single tenant. Ideally, if the developer can get a single tenant, they take the whole building, you can almost do something like a build to suit for them. Obviously, you can design it around that, but you're a real estate developer, you're taking on some risk. Maybe you're building some of these things speculatively. you're trying to attract a variety of tenants. Like, how do you work through that as a developer to make sure that the base building design can accommodate the different needs of these different types of lab uses?
Yep, certainly. So I think it's back to that point that Tyler was making, that there's a lot of different requirements that certain labs have. And I think it depends on the type of lab that you're sort of doing the building for. And so like we typically do BSL2 plus, nothing higher, unless it's something that's more purpose-built. So in that case, in that sort of mindset, there's a very prescriptive, type of building that you would do. So for example, this building on the left, the research building, it's, your typical, facade system, unitized curtain wall, nothing too much extra from a sense of doing something to get to those requirements that are needed. And then we try to kind of balance that, the specifications and everything that we build the buildings to, so that we can attract the widest variety of tenants, or provide some sort of design that is very adaptable to, the majority of tenants. We might not be able to house, someone that is heavy chemistry in this building because it wasn't set up for it. So then we kind of look to the next building for that. But for the most part, when we start a project, we typically have an anchor tenant. And so they take about 50% of the building, 60% of the building. So we know right off the bat, who we're actually kind of designing towards. But at the same time, we just can't think of that first generation tenant. We got to think of second generation, third generation, and how does the building adapt to all those tenants in the future. And the other part of that too is, good design, right? Good facades, attracting good tenants, and using the design from the architects. And sometimes it might be a little bit of premium, but that's how you attract top tier tenants to these buildings. And so, for example, this building on the left, we used these, it's a unitized curtain wall system with these metal fins or metal panels that go on the edges, and they rotate whether they go left or they go right or they're flat. And, a perfect example of that is, let me go to that. So there's a little picture of it where you can see the unitized portion. They came with the unitized system, but if you go to the detail, nope, that doesn't work. So you can see the triangle at the very top and the detail on the top. That's the little triangular piece, a metal panel that went into the curtain wall system. And when we first started the design of this project, there was a lot more of that around the entire building. And when we did the cost analysis, we said, well, that's, it's a little bit too expensive. We can't really afford that for the type of tenants and clients that we have, the market that we have. So this is Charlotte, so you got to think differently than you think in Boston. But we did a sort of analysis of like, okay, well, what if we reduce that amount to 80% or 60% or 40%? And after doing that analysis, we came to the conclusion that, going down to 60% of those white fins being protruding in triangular shape made sense and worked with the budget. And in fact, actually, once it's been built, I feel like that actually helped the design instead of having it, be all the metal facades or the metal panels be protruding. So that's, a little bit of a snapshot of how, we attract tenants and really top tier tenants.
Okay. I think we'll circle back to John. So back on the assembly, you sort of hinted at and sort of alluded to some of the structural challenges with the enclosure. I'm just curious to hear a little bit more about how you dealt with those, and how some of what you did sort of was impacted by the life science nature of the facility.
Yeah, so I'm gonna talk about the crane shed, and then I'll talk about the Ford building. But to look at that, the crane shed, it's a steel structure encased in concrete, and this is what we found inside on the right side in 2018. So there was a big task to really dig into this and see what we had, what could we do. And I would say one of the bigger constraints that we found with this structure was the physical structure. We had to rebuild about 50% of it, the entire south facade and the entire roof, and then we had to do a lot of heavy repairs on the concrete encasement. You can see here some of the framing going in, and yeah, you can see a lot of repairs on the concrete, and we had to do a lot of invasive work on the structural connections. So there was quite a bit of invasive work that was done to get this shell, up to, just up to snuff, not even, high performing. And what we found was on both the forward and the, let me go back here. On the forward and on the crane shed was, we studied different insulation strategies. So you can see lower left here. That purple line represents the relative humidity on the inside face of the wall throughout the year. And going into this, we all thought, hey, we need to insulate this building, because it's a laboratory, and we know we're going to put a very high performing window system in. But what we found was, wrong. We shouldn't insulate the building. It's a 3-weight, 14-inch thick solid masonry wall, solid collar joints. So that was I remember when we kind of came to that conclusion after a lot of analysis, everyone was like, can we do this? And National Park Service regulations basically tell you cannot insulate a building if it's going to harm the fabric. So it's something to keep in mind when you're looking, on adaptive reuse. On the Ford building, same issue. We also had on the restoration side, on the facade side, some of the things we ran into, were issues like the smoke control of the atrium. I'll go back to that picture, but we were able to integrate. We had a very big smoke control system in the building. We were able to integrate operable lights. You can kind of see them down on this level to bring in our makeup air. And of course, the goal was to keep this, keep maximum daylighting throughout the entire, building, the entire space. And using this wall, the interior wall, also glazed. It's a 1-hour wall, smoke-tight wall. That was also part of the whole glazing and shell approach to the project. So, I think big takeaways, when you're looking at a building that could potentially be an adaptive reuse for lab, look at the bones of the building, look at the superstructure, look at the floors. Can they take the vibration criteria, the MIPS criteria that your lab use is going to demand? Look at how the building would lay out. What kind of user do you have? Do you have a user like Daniel was speaking to? Is it speculative, or do you have an end user? Understand their requirements and how they're going to interface with that structure, floor to floor heights, the column bay, spacing, getting infrastructure in, through the building. All those, and these aren't all necessarily facade related, but everything has to meet that facade. And if it's an historic building, it can be very challenging. So, I think it was Tyler was speaking to the whole issue of, humidity. There are spaces in this building that have very high relative humidity, and we absolutely had to insulate them. They're on below grade levels, but we had to strategically put them on below grade levels because of that issue. Some of them wanted to be on above grade levels, but we just couldn't do it because we'd have a big condensation issue. So, those are some bigger takeaways that we gleaned out of this project. Yeah.
I think one of the things that we always consider too is that when we do the buildings or go for a building, we try to meet LEED Gold as a minimum, or try to strive for further sustainability measures. In certain universities like that we have go for, maybe wall standard. So that all plays into the type of facade and systems and insulation that we use on, whether it's an adaptive reuse that we go for LEED or a new building that we go for LEED.
Yep. Hey, John, for the windows of this building, was the historical aspect of those windows controlled at all by what types of materials you could use?
Yeah, great question. We absolutely had to do fully, you can see here, fully thermally broken. We had mutton grids, between the two glazing panels, and then we had applied muttons. So yeah, these were really specialized windows, and we talked to a lot of manufacturers, and Wausau really came through. They worked really closely with us, and we were communicating with them from day one for all the openings. And really critical part of it was getting these windows in the sizes we needed, and every window was a different size, because all the openings were very different. So it was a bit complex to get there. But another footnote, just from a design standpoint, the addition was really, the geometry of the addition and the materiality of the addition was really informed heavily by the original building, and we really wanted to complement the original building, so we brought terracotta in. Terracotta was looked at. Turner told us, put it on precast. It's going to be much more economical. We found into the process that that wasn't the case. The structure had to be upgraded substantially, and labor in Pittsburgh wasn't quite that high, so we were able to get a rain screen. But the fenestration on the addition, we really tried to meet a window wall ratio that the Wexford team wanted us to hit, and also be responsible. But the addition is very, very flexible. Wexford wanted it to be a very flexible, partnering research space. So that's how it was designed. And I didn't mention also this project has 3 retail corners in it, which was another nice thing that we tried to do for the community and with the developer.
Okay, I think we got time for a couple more quick ones. So we'll go back to Tyler. So we've heard, I think you mentioned it, John just mentioned it a lot, like the challenges related to moisture and temperature management with the exterior envelope. Are there certain strategies or technologies that you found that are sort of the most useful in trying to manage that in these life science facilities?
So I would say that there's just such a robust amount of systems out there now. This is primarily curtain wall at 9950. This is a combination of curtain wall and brick. This was actually a cement fiberboard with curtain wall and as a rain screen system. Again, another example of curtain wall. And then you've got one that shows a combination of curtain wall, storefront, and brick. And we sort of intentionally are showing, all of the different systems that can be included. This was actually a prefabricated structure. You can see that on the right side image, the exposed structural beam that's in there. And this had like a corrugated metal on the outside. And then I think finally we've just got an example of corrugated metal storefront and brick. And the point to showing the diversity of that is to say that I think when you're detailing these buildings, no matter what system you're using, the most important thing for the architect is just to have an awareness of the continuity of that weather barrier that we talk about, and then making sure that your insulation is continuous across transitions between curtain wall and brick, or curtain wall and metal panel. Oftentimes, the way that you draw it at your desk, the way that you envision it in your head, when you go out to the site and you see the way that the connections are made, you realize that there can be gaps, right? And all those gaps are opportunities for infiltration of that exterior air into the building. so you always have to be careful, and you always have to be cognizant of, is what I'm drawing based in reality? That's critical. I'd also say about the exterior installation and insulation and the continuity of that. You need to make sure that when you're hitting jams, when you're terminating at heads, that you're always wrapping those corners. Mm-hmm. And then if the interior wall is a part of that overall assembly, there could be cost savings instances where maybe you don't carry that insulation above the interior ceiling, but then you're opening yourself up to an issue in the interstitial space, right? Or an issue above the ceiling. And oftentimes it's those overlooked conditions that bite us, right? And so, just as a lessons learned, like I've been on jobs where we've retrofitted buildings, they've had exterior walls, and, that area above the ceiling gets overlooked, and that allows moist air, hotter air to get in, where for a laboratory, very cold 60-degree air is moving through ducts, right? And you know what happens when that warm air hits the outside face of those ducts. You get water, you get sweating, and that drips down on the ceiling. So you have to think about whatever system you're putting in place. Am I detailing it continuously? And the simplest way to do that is always the best solution. So avoid, multiple different systems. There are metal panels that act as both the rain screen and the weather barrier. I would still recommend that if you are using a combination of that and a rain screen system, that you run continuously your weather barrier even behind that system, because it's just going to give you that peace of mind. So.
All right, we got time for one more. I'm going to go off script if that's all right. Okay.
That's fine.
You got like a minute to answer this, but I'm curious, as somebody who used to be an architect and now works for a developer, how has your sort of perspective changed about the design choices on the exterior envelope now that you're sitting in the developer seat, where you used to be in the architect's seat?
That's an interesting question. It's and I'll try to answer this pretty quickly, but I think I bring a different perspective to the developer side, just because I know what goes into a good design. I know what goes into a good facade. I know what goes into making a building, great, right? And so I also have to balance that with the cost of the design. And so I think one of the things that we were going to talk about too, and I'll kind of push forward, is that design assist for us is really helpful, because then we can bring the partners in early with the architects and analyze a lot of different attachments, a lot of different mullion systems or facade systems. And especially during during COVID, where lead times were really crazy, it really helped us. But it helped us also weigh the cost of the projects. And so when you're looking at it holistically, I think I'm starting to be a little bit more cognizant of that, but at the same time also helping my colleagues see the benefit in certain elements of the what we're choosing that really will go, for the long end, get a really good tenant. So for really caring, just kind of going forward, we have a lot of different systems in these buildings, unit-sized curtain wall, we have terracotta, and I think that leads to the schedule as well. And so kind of leading with the schedule, that also plays into it, is how quickly can we get to the market, and, having that schedule. And I think that my background really helps with the design teams kind of evaluate different designs and attachment methods, or not necessarily attachment methods, but what the building is made of, quicker than someone that doesn't know design at all. So having prefabricated panels on site, curtain wall system, rain screen, terracotta system, and so kind of helping others understand, yes, we're doing sustainability, so we do green girt, and so kind of trying to get that a little bit more than just your generic bottom line dollar.
Great. Okay, I think we're at time, so I think we'll wrap up there.
Thanks. Could the speakers for this last session come to the stage for photo ops when you get a chance? And just a reminder, no lunch in the room. We'll see you in about 50 minutes to close out the day with session 3. A lot of great speakers coming up, so we'll see you then. Thanks. All right, welcome back, everyone. Next up, this is another cool project. I love this project. I'm going to introduce Jason Wu. He's an associate with Big Architects, and he'll be talking about the Bloomberg Student Center, Johns Hopkins University in Baltimore, Maryland.
Hi, good afternoon, everyone. Thanks for having me. I'm Jason Wu. Again, I'm an associate at Big New York, but we also have offices in Europe and Asia. And I'm very excited to present the Bloomberg Student Center. It's a project that we started as a competition in 2020, but we won the competition and it finally got completed in November. Like many of our projects, it was really truly an effort with our incredible collaborators. As it is facades, I want to give a special thanks to Johns Hopkins University, our client, for giving us the opportunity. Shepley Bulfinch, our partner architects, Nippers Helbig, our engineers for structure and facade, structure craft and timber assist, Littner on the curtain wall assist, Clark on the construction, and finally WJE for the enclosure commissioning. The theme of this project is architecture as a landscape, how a mass timber commons can transform the university to become the social heart of the campus. And for Hopkins, this is truly a once-in-a-generation transformative project. In its 150 years of history, it has never had a student center. So there has been this long yearning of students wanting to create, wanting to kind of live in a social space such as this one. And maybe just to give a little bit of context, the site is located in their Homewood campus in Baltimore, Maryland. And then you can see here, although the site sits on the edge of the campus, it has become the sort of center point where students have come to gather. The Homewood campus is characterized by its Neo-Georgian brick facade buildings. Although it's beautiful, it could seem a little bit enclosed. But the brief that we got from the client was very different. They don't want a classroom, and they don't want a lab. They want to design sort of a non-academic space that students can come and relax in between classes. And these spaces exist already on the campus in their outdoor quads. These kind of open, informal type spaces that the student culture come and thrive. Unfortunately, this is the site when we first visited back in February 2020. It was the biggest downpour in Baltimore that we've seen all season. A month later, the pandemic happened. So almost like a sort of a tragedy, we began to speculate what this new social space could be while we were isolated at home. So we knew right away we wanted to create a quad at the same scale as the beach next door. Something that is open on all 4 sides, that connects to the exterior pathways. And student culture, once dispersed behind closed doors, find its home at the edge of the campus and becoming the sort of gateway to the community. So in a way, this is the concept. Displaying the sort of physical manifestation of the student body diversity onto the facade of the building. This is one of my favorite photos of the entire project, which you can see the sort of duality between the campus beach next door, transforming into this new space on the new intersection of the main streets. The project is conceived as 29 cascading timber roofs that gently rolls down the surrounding landscape, and it really opens up to the surrounding streets. And the building really has no back. Every pathway is a destination, where you kind of formulate it into commons, plaza spills out on the south, the rival entry towards the east, congregating in this kind of central focal point. And the building is stepped on 4 levels. You have direct entry at all parts of the building, creating one of the most accessible buildings that we have seen on campus. A question that I get a lot from the client and the contractors is why 29 roofs? And it really is a sort of a very comprehensive programming effort led by Shepley Bulfinch, which had a research of nearly 1,500 students contributing to what they want in the Student Center program. So straight away, we knew that we wanted to let the program drive the section rather than forcing it into a box. And we quickly realized that nearly half of the program, the black box theater, the loading dock, the back of house, they don't require daylight. So we kind of neatly leveraged this topography and tucked them underneath, which allowed us to put all the social open programs up above. And in a way, it created the central living room, which I'll get into a little bit later, but it became the sort of beating heart, not only for the building, but for the entire campus. The building is very open and transparent, and it looks different because it performs different. Here you can see how the transparency juxtaposes itself onto its brick neighbors. And on the street level, it really becomes this welcoming kind of gateway of openness and transparency. And because of the building steps down towards the street, even though it's a 4-story building, it has a very human scale as you kind of walk in and around the building. The alternating glass and anodized aluminum panels alternates to create this very ethereal effect that reflects both the landscape and the surrounding landmark, as perfectly demonstrated here, the way the facade almost disappears. And glass for us, it is a material. It is such a dynamic material that sometimes is present and sometimes is absent. Sometimes it reflects and sometimes it's transparent. This idea of lightness also translated into the way we think about the details, where you can see the corner mullions captures the glass-to-glass connections to create a very, very minimal framework in and around the building. Where the glass meets the metal panels, a knife edge detail that really kind of slims down that corner connection to reveal the timber structure and the student activity behind it. The facade is a stick-built curtain wall system with laser-welded steel mullions to keep a very, very slender profile, because transparency and openness and porosity was so important to us, and it was even in the base details, we try to keep that datum very, very minimal. And it was important to us because the entire site slopes. So here you can see the building really gently rests on the sloping landscape. It's not a building that sits on a plinth, which allowed us to put all the student activities very foregrounded and on display on the student campus. So here's a wonderful image just showing how the students walk in and around the building, kind of having this direct vis-a-vis to the interior programming, where these brick pathways gently guides you into the building. So in a way, the building itself presents it as an invitation to step in rather than a barrier to cross. Another inspiration for the project is the fact that it sits next to the woodlands, right? For us, the forest is the sort of ultimate expression of a serendipitous, open, and natural environment. And when you look up, you see the sort of light filtering through the canopies of the treetops. And it's this feeling that we really want to recapture into the interior, where upon entry, you're welcomed by a forest of timber columns and glulam beams, where wood as a material is such a warm and tactile surface with almost infinite depth that it became almost like an antidote for students being stuck in classrooms and labs all day. This is one of my favorite rooms in the entire project, the dance studio. Here you can see how the beams and posts encapsulates this wonderful space, acoustically tuned to perfection, and with direct vis-a-vis both to the inside and outside. And I will say, like, when you're inside the building, sometimes you forget that you're indoors because of how open and transparent it is. The roof planes we detail such that it extends inside the building, creating these kind of cavities for us to conceal surfaces. The clear story glass is triple laminated units, which allowed us to eliminate perimeter heating around those clear story moments. Not only was it more cost effective, but it also decluttered the roof plane, which you can see when you're standing on the 4th floor. So in a way, when you take a step back, the roof almost feels like it's floating with the sort of lightness that these kind of design kind of became. But of course, designing 29 flat roofs was a major challenge, as you can imagine. So our team created drawings and tools for us not only to track all the hidden elevations, but make sure that all of our facade modules are in check to minimize atypical conditions. This allowed us to align the structural grid and the curtain wall grid to hide as much of the framing as possible. The team even went as far as to align the sprinkler heads and this sort of obsession to alignments. The timber structure done by nippers was created primarily with mass timber structure. Here is like a raw photo. Excuse the temporary bracing, but when you step inside, it feels like you're within a timber cathedral. But because of the fact that it's wood, it has this sort of softness that makes it feel more intimate, even though it's such a monumental space. This is the span across the living room. I'm always impressed by the sort of the length that the wood can achieve. This is 70 feet in length. So when you're standing underneath it, you can feel this sort of almost like a defying gravity moment that the timber structure has. I love this image too because it showcases that beautiful symphony of how all the connections comes together. It almost showcases the craft between construction, engineering, and design all at once. Together with our friends at Nippers Helbig, this is just one of the diagrams that they created showing how the joineries come together, almost as a sort of incredible IKEA kit or manual that you can do it yourself, but of course with the precision of German engineering. And this is just a diagram showing how it all comes together with these nice timber slabs coming on top. Here's a photo of it under construction. In the few moments of the project, we do have solid walls. We packed them with services because there was just such a limited opportunity that we had them. But another thing that's challenging with such a glassy building is thermal heat gain. Thornton Tomasetti did an environmental analysis for us, tracking which facade receives the most heat. Even before getting to glass performance and products, what we wanted to do was create passive shading strategies with these timber roof planes. Together with StructureCraft, we selected Dow laminated timber. Unlike CLT, DLT is basically a series of lumber planks that allowed us to span longer in one direction. But it also allowed us to integrate some of these services with conduits and AV systems, as well as acoustical attenuation. I think this just showcases the depth of design and coordination that really went into the project. I think one of the victories or major successes of the project is actually the things that you don't see in the project, but you absolutely feel. Because removing ductwork and all the sort of machineries that makes the roof feel heavy, when you look up, you sort of feel this lightness in the ceiling. And that feeling, I think, was one of the sort of biggest testament that we had to the design team. On the rooftop itself, we cladded it with nearly 1,000 photovoltaic panels, which powers half of the building's electricity. Mass timber, as you know, is one of the most sustainable way to construct a building with its ability to sequester carbon. So sustainability for us is not just a word we throw around, it's something that you feel and experience as the students walk around the building. And finally, the student living room, the campus living room, this sort of cascade of informal landscape, creating pockets of seating and student activity. Here we welcome our first users into the building back in November. And I think it was Rand Koolhaus that said, the building has at least two lives. The one that you designed and the one that the building lives in after. So in a way, I'm very excited to see how the student starts to transform the space. So this project really is about how architecture can perform as a sort of a natural landscape to create this very informal space, but also acts as a forum for mass critical gathering. This is a photo of Bjarke Ingels, our founder, giving his opening address to the entire campus that showcases how this space can transform into this informal gathering space. So for us, this project, as much as it is about that monumentality, but it also has a sort of intimacy of these individual groups that really comes together to celebrate this project. And the openness and porosity and liveliness of the activities and the timber structure creates this almost like a welcoming gateway that really showcases the sort of ever-changing mosaic of the student body and the Hopkins community, becoming sort of this village that is greater than the sum of its parts. Thank you.
I always think it's so interesting too with mass timber how the understanding of its behavior in fire, and modifications to the code and the willingness of the industry to look deeply and to understand that deeply has allowed it to be exposed like that. Because if not, you lose, the impact of it, which I think is huge. Next up, we've got Roman Schieber. He is the managing director of Knipper Schalbig, and Michelle Lee, architect with Behnisch Architekten. And they'll be talking about the Energy Science and Technology Laboratory, the GELOS, I think, and the Well-Tempered Lab. So, thanks.
Good afternoon, everyone. I'm thrilled to be here with Roman. With you here in DC, my hometown. So I'm joining from our office in Boston, Massachusetts. And I just wanted to start with a little bit of context before we jump into this facade for this particular project. So for us at Behnisch Architekten, we try to find always the overlapping patterns for existence between human and non-human life. So our architecture is very much about a process of exploring other life forms that informs and shapes our built environment. Okay. So I think it's helpful to start with some scenes from our office, right? For those of you who aren't familiar with our firm, we kind of grew out of a central office from Stuttgart, Germany. And in this part of the world, there's a very strong environmental movement that emerged from the post-war era of Germany. But it's also important to point out that they're also shaped by a very strong engineering culture. So if you think of all the German cars and kind of high-performance equipment is coming from this area of Europe. So I was really surprised during the Olympics when the Milan Cortina skating rink didn't have any daylight. We always try to put daylight even in these challenging environments and integrate kind of advanced new technology in order to further the performance of the building. Just introducing Roman. We've been working together for as long as I can remember. I think I've worked on 3 projects with Roman so far. And he works with Big, Renzo Piano, just some scenes from their office so you get a feel of the vibe. So this building is a new facility for energy science and research. And it's at the University of Pennsylvania. It was also started during COVID. We won it through an invited RFP. And this is just an interesting example of one of the threads of research that's going on in this new building, right? It's all about how you extract cobalt from e-waste. So cobalt is a critical mineral in battery energy storage. So how do you prevent the kind of extraction of this mining that is inflicting great suffering in the Democratic Republic of Congo? So the site for this project, super interesting. It's in Philadelphia, so 2 hours north via Amtrak or car. It's about a 10-minute walk. The campus is sitting, sorry, oops. Yeah. The campus is, wait, is this pointer working? Okay, sorry. I will maybe not use the pointer. The campus is sitting to the left. Our site is, in this yellow box. And it's really interesting because the site is kind of in between the city and the university, and also critically right next to the Schuylkill River. If you guys are familiar with Philadelphia, the campus of UPenn is kind of cut off from the river, right? And it's cut off from the rest of the city because they decided to build a highway, like going right down the West Bank. So a lot of this project was about stitching this connection, reducing this perceived distance between the university campus and the city, and kind of restoring the connection back to the waterfront. This is a view looking at our building coming down from Walnut Avenue. In Philly, they named all their major streets after trees. And it's all about using the facade and showcasing the energy research of the city, which I find a very important task to do in a city like Philadelphia. If you think of Philadelphia, it was the birthplace of the American Enlightenment. If you know about Benjamin Franklin's work about using many different types of scientific research to, better the middle class, the everyday American. So, a lot of building types are probably better at this kind of civic scale, like museums. But we were interested, like, how can we make a lab, have a civic presence? So has anyone watched this Netflix show, The Madness? We were really excited that they decided to shoot it right in front of our building and have the protagonist run across this bridge that is, it's like, there's a lot of concrete, there's freight trains everywhere, there's a lot of infrastructure. So the fact that we can get people to move across the city with the building, for us was super important. This is shot facing the east side of the campus, right? So there's two kind of very different expressions, the labs facing the city and the social spaces facing the campus side, right? So it's quieter, there's more green. The scale of the urban fabric is different, so we have a different, expression to address that. We also use the massing on this side to introduce a lot of green spaces. The researchers really wanted to have private green spaces so that they could relax and have lunch. So the kind of programmatic distribution, right? Urban versus campus, labs versus the social space. This was very much kind of designed in tandem with the energy strategy, right? So we wanted to put the labs facing downtown because it's loud, so we're having a more sealed facade, a more controlled space. To the left, we put the social spaces, which I'll go into later, and then the big idea here was that the facade could be more porous and open, right? Because it's facing the university, more pedestrian, more trees. It's like our major space for passive systems and natural ventilation through the building envelope. So just to show you like a peeled off kind of dollhouse view of this social space that's facing the campus, the central area where we centralized a lot of the passive systems, you can see the kind of little cells are the faculty offices, and you can tell that we pulled down the partitions and then put the clear stories in glass in order to create a sense of openness and dialogue between the researchers and the students. And then also these double height spaces that you see. I'm going to try this pointer one more time. It's the stop button, right? Wait, every time I do that, it's like, okay, sorry. Okay, forget the pointer. You can see these double height staircases that kind of stitch the different floors together. I'll just show you a few photos really quickly. So these clear stories that bring the daylight through, and then these social spaces and the faculty bank of offices in the center. We worked with a very narrow footprint, and we wanted a slender lab in order to bring daylight in. So we were left with these very kind of east-west facing facades, which, as you all know, as facade people, they're the hardest to control in terms of solar heat gain, right? So the idea for the facade was to really temper these extremes of the sun. We also, in addition to tempering the solar heat gain, we had to deal with daylight and glare. So these kind of shades that temper the daylight were also important in mitigating glare from these orientations. So we actually were really inspired by the campus architecture, and we looked at a lot of state-of-the-art labs that were built during their time. So these are two examples at Penn from mid-century, right? So the left is, your kind of typical mid-century lab with the kind of glass clear story blocks, which kind of diffuse light, and then a little vision window. And you can tell that it's like totally designed in a passive way through the facade in the 1950s. You have these horizontal sun shadings facing the south, right? Super smart. And then the one on the right is, I don't know if you guys are familiar with Louis Kahn's Richards lab, which was like the state-of-the-art lab in the 60s. But we had a lot of discussions with the scientists, and there was a lot of issues with solar glare and solar control. So you would go past it, and it would be covered up with foil and cardboard boxes. I don't think Louis Kahn really would have been happy. So we kind of took these lessons, learned through generations of other designs. And what we did with the east-west exposure was to bring back this idea of the clear story that's dedicated for daylight, and then introduce a kind of smaller operable right at the bottom, this lower vertical piece of glass. And then that gets us to a more responsible window wall ratio. This primary facade type, I think, was around 50. The other ones have less glass, okay? And then we used these two types of membrane materials, which I'll get into later. But the top one is really about bringing in the intense daylight and then diffusing it so that it's like less harsh on your eyes. So it's a little bit like a frosted, when you frost a light bulb, it kind of distributes the light more evenly. And then the bottom panel is dedicated to providing a more vertical kind of sun shading for that bottom pane of glass. And we selected a 70% fritted silver dot in order to reflect, 70% of the solar heat gain, but still maintaining that view and that transparency that was important. Just some studies that we did with Transolar, testing the different architectural fabrics, right? I don't know if you guys have worked with the fabrics, but there's many different types. There's PES, PTFE. There's a whole wide range of materials that we thought was important to test just passing, sunlight through an oculus and measuring how it disperses light. We were also really interested in understanding the relative embodied carbon between the top three, which are the membrane materials, and the bottom two, which are your more conventional shading materials. So what we learned doing this study with Roman's team at Knippers Helbig was that the architectural membranes, because they're like 0.2 millimeters, they have a much lower embodied carbon over the lifetime of the building. And then we calculated, for the client that this would be paid back in carbon. The embodied carbon would be paid back in 1 year with the operational carbon that's saved, right? So lower air conditioning, less energy in order to cool the building. And then we also did a life cycle analysis, understanding the different chemical compositions of the different materials. And we selected the top one, the ETFE, that you can see, which kind of performed kind of the best out of most of the materials. We didn't want to use any materials with Teflon or any fabrics that couldn't be recycled. I still think there's a lot of room in the industry to innovate on using very strong, thin materials that are also healthy and have a good chemical composition. The fourth one from the top, I want to point out, it's called, it's like silicone-coated fiberglass, right? So it actually had the healthiest kind of overall picture, but we couldn't find a fabricator who could do a project of this scale. So I'm a huge believer in tensile fabrics, but I think there needs to be more research, and it's a lot of potential in this line. Just to see everything together inside one of the faculty offices, using the sun shading allowed us to use radiant heating and cooling. You can see the kind of clear story kind of migrating its way inside the building, all out into the hallway. So this kind of holistic integration of facade all the way to the user, how the user can kind of see out. Our intern forgot to make the window on the bottom operable, but that's your Schuko kind of casement window that we used. And then this is just an integration of all the systems, right? So you have the left passive systems on the campus side with 40% natural ventilation, right, using this climate of Philadelphia. And then to the right, you have the kind of high energy lab and a more sealed facade. This is just a funny picture that I took where the kids are like using their cell phone as sun shading, which I thought was funny. And then, just understanding that different facades need different orientations, right? Because they have very different exposures to the sun. This is your north facade. Obviously it's a lot simple, not as stringent. And then what that feels like from the inside, right? Experiencing two solar orientations in the corner. Just want to point out that, the ducts at the top they're like 4 inches because you're using radiant heating and cooling, so you're reducing the size of the MEP. Roman.
Thank you, Michelle. We'll see what she left over for me. So just for context, our two firms have done a number of projects where the facade is both architecture defining and highly energy efficient, and both things are coming together, creating unique architecture. So the goal was set from the beginning when we started working on the project. I think we knew the budget from the beginning, around $250 a square foot, what is quite fair. So we had the chance to try out options, designed the facade to budget, I think. As you can imagine, we have had a number of different wall types, but I'm going to focus on the east-west facade, the main facade here. So there's mainly curtain walls, some storefront, stick-built, also some mega panel facades. So from a facade engineering standpoint, for this project, for this facade, the engineering perspective of the shades was one of the most the trickiest thing, probably. I mean, it's huge sails in the end of the day. It catches the wind. We had wind loads of, I think, a bit more than 50 PSF at the top corner somewhere, leading to high reaction forces. And we had an aluminum curtain wall, you will see in a minute, and how to transfer the loads through the aluminum, which can be considered almost non-structural, to the brackets. Another topic was when we developed the shades together, we tried out many options. And I mean, a fabric doesn't want to be flat. It cannot be twisted too much. So we always had to check the geometries. What is the cut pattern that it can be fabricated, that it's properly tensioned. As said before, we ended up doing not sure if I should say traditional curtain wall, but at least it's a relatively normal curtain wall approach with prefabricated panels hung to the brackets and these features in front. Pointer here. Yeah, this is.
I don't know why I couldn't figure that out.
See that, Michelle? Yeah.
That's why he's the engineer.
So introducing the forces close to the facade bracket was the goal, but due to the geometry, we always had some points where it's more at mid-span or a third span. So the load transfer to the brackets was always what we had to keep in mind. Another topic, as said before, highly sustainable building was always the goal. So when you build a building or design a facade, there's different lifetimes for different components. A superstructure has typically a longer lifetime than a glass facade, a spandrel panel. The glazing and the ETFE, the material we ended up with, has maybe just a 20-year lifetime. So the goal was to design all the details that it can be dismantled, taken apart for circular, in sense of circular construction, bolted connection. So if the ETFE has to be replaced at some point, maybe there's other or even better materials. In 20 years, you basically can just attach the new material to the existing frames or to do something completely different. So the facade system, this was a detail we developed before we went out for bid. It's maybe not exactly what you typically see on North American projects, but the background is that we had these knife blades going through the vertical facades, the loads, which had to go to the brackets, and as the loads are traveling up or down to the brackets, we had a little chamber. The pointer is awful. Here, with a stainless steel spigot in the chamber, which allowed us to transfer the loads vertically down to the bracket. Yeah, that were early studies for the framing of the shades. That was an option we studied as aluminum frames. In the end, we decided to go for steel framing because it's simply slimmer, smaller due to the higher structural capacity. So it wasn't a linear process. It was always trying out options, and so that's also 3 different approaches with steel, with aluminum, with different clipping details systems. That were actually the very first kind of visual mock-ups, which are simplified details, other details, but getting a sense of the scale. On the left, I must say that I think the client at some point, they were not completely convinced if ETFE is what we should do, what is about durability, will birds maybe, I don't know, start eating the material. So perforated metal was at least an option. We never preferred, but it was built as an option. It's not the same performance-wise because it just blocks the sun, but it's not a diffuser when you look from inside. So that were another, I think it's not the same, it's different visual mock-ups at Penn University, just next to each other, and then the decision was finally made. I think we can make that quick. Construction documents that were, I mean, we did both structure and facade engineering, so coordinating the interface details, load transfer, tolerance adjustment, it was just homework. Maybe just one exemplar detail of a corner with on the left, the main facade we were just talking about with the external shades transitioning into a different wall type. I think this is the it's the north facade with some lamellas, opaque panels, but it's based on the same curtain wall system. Then we've, during the bidding process, we ended up getting Lindner facades for the project. The facade system still followed the concept, was slightly modified as they had some systems, and it was an in-between solution, I'd say. On the right, it's the final framing of the curtain wall, but also of the shades. That's the as-built details. It's basically still exactly the same what we had designed before, and maybe you have figured that on one of the facades we have these volumes coming forth and back, so we had not only one typical shading element, but also ones which are basically cut or under the overhangs. So different geometries, interface details. There's so many interface details Michelle has designed and finally had to be built, but went quite well. The curtain wall units have been fabricated in Arnsdorf in Germany by Lindner. The interesting thing might be that all the material, the glass, the framing came from a very small radius. I mean, shipping overseas is maybe not great, but it's just around 2% of the carbon footprint. So it's an okay number, maybe. And as I said, maybe interesting that the material really comes from a close radius and has been shipped. These are the crates, the timber crates with the panels, 3 panels per crate, and I forgot the number of the containers, but that's at Vector Voltec was supplying the ETFE material and shades to Lindner. On the bottom right, maybe you can read that it's all recycling ETFE. Also interesting that ETFE on its own has a good carbon footprint, but in that case, it's even recycled material, pre-assembly. That was outside
Colmar.
In Colmar. It was in Colmar, where basically the shades and the unitized curtain walls have been married, shipped on site, and then with a tower crane they have been lifted in. So that went quite smooth, I think. For the units under the overhang, they had a special tool, so just that it had a small cantilever allowing for the installation under the overhangs. So looks like plug and play Lego. It really went well, at least on the one flat side. It was easier than on the other with the overhangs, to be honest. And maybe you have noticed that there's a distance between the shades and the curtain wall. That's for maintenance reasons. If you're wondering how to clean it, there's a distance where you can go in between from the top to clean and maintain the facade. Still installation, stacked joint gasket in the next unit. And we have a video. I think it's 2 minutes. Michelle, you have to say something now. How was it working on the project, Michelle?
It was great.
Good.
I mean, this is just a good way to see the kind of urban context I was talking about, the tight site. You can see on the bottom under the armpits that we didn't install the shades until after, right? Those had to be installed not with the curtain wall units because you couldn't stack it from the top. This is the south facade that we never talk about because it had mostly cores and bathrooms. And then you can see the horizontal shades, right? But you know, the primary facade types are the east and west because those are the ones where the program is and it's bringing in all the light. Yeah, we're holding up the traffic,
and a little chessboard pattern here, just to, show that not everything's perfect.
QC Facades is here, so we wanted to thank them. You can see the giant louvers on the top. That's like the lungs of the building. That's for the air supply. That's supplying air to the labs. I always thought that louvers should be celebrated more in architecture, especially for labs, because they're doing a lot of the hard work. I think that's good, Ramon. So in conclusion, we just wanted to thank all the, the client and the researchers that are researching for more sustainable forms of energy. The facade was really designed, to support their research. So thank you very much.
Thank you.
ETFE is such an interesting material. They say that it's got a high surface tension, so it also is supposed to shed dirt, but it also has like an inelastic deformation during a period. So I wondered if, anyway, I'm going to ask you after because I'm curious. I know when we did a project with ETFE, it will deflect and it will not come all the way back to its original location straight up. But next up is Amanda Stacy, AVP, Building Enclosures Department Head at WSPDC.
Hello, good afternoon. Can you all hear me okay? This is a little bit to get used to, right? Good afternoon. My name is Amanda Stacy. I am, as part of WSP, our department head for our building enclosures group here locally in the DC market. And I'd like to thank the whole Zak team for inviting me to chat with you all today about our experience with design considerations for office to residential conversions. I think I'm going to need this. So office buildings were not originally designed for residential performance. There's a little bit of a difference between the two uses, when it comes to comfort and use, durability and code. And it's important to perform feasibility assessments at the start of the project to see, hey, is this something that we can even proceed with? And many times it's required for, financing and funding purposes. We want to take a look at the feasibility from spatial planning, amenity potential, MEP, fire protection system integration into the building, but also including our building enclosure. The building enclosure can have a major impact on these type of conversion projects, not only because it drives cost, risk, and constructability considerations, but we'll talk about a lot of those considerations here, but it can really help to set the project trajectory and determine if the project's going to be a go or a no-go. Within the DC market, we have high office vacancy, high residential demand. We're one of the leading markets in conversion projects, whether it's office to residential, to hotel, to other projects. And there are local government supports, for tax incentives or other policy supports for owners and developer teams to help make these projects a reality. As you can see from the map, a lot of these conversion projects are concentrated in our downtown and core submarkets. And so a lot of times, because of that creates some complexity with our building enclosures. We may have pretty slender sites. We may have interfaces with neighboring properties. It could be, 1, 2, 3 sides that we need to interface with, and also our interface with the public. And so to kind of start this, we recommend a fully comprehensive condition assessment. And that condition assessment shouldn't only include building enclosure, it should include all of the disciplines. So architectural, you get into engineering and structural and specialty disciplines to make sure that we're getting a truly holistic view of the feasibility of the project. From a building enclosure perspective, the scale could be, maybe a little more high level, or it can be down to, the detail of, noting exact cracked locations and where those are all located. And so from what are we looking for as part of the building enclosure condition assessment? The building enclosure is what separates the interior space from the exterior space. This includes our below grade spaces, above grade vertical facade, our opaque wall assemblies and our fenestrations, and our roof assemblies, and of course, all of the complex tie-ins in between. And so it's helpful to understand as part of the assessments, one, what are the systems and materials that are in place? What's the current condition of those particular systems, and what do we need to do from a repair, restoration, and replacement perspective to meet the project goals? And also, are there any opportunities from a design perspective that we see through the building enclosure that we can recommend to the design team to really enhance, the look and the feel of that residential use change that we're going for? So one of the things to consider are, existing versus demo to grade. When we're maintaining the existing structure, there are some, it can limit the flexibility of the project, as it pertains to the floor plates, as it pertains to the building enclosure itself, and what changes we may or may not be able to make depending on time and budget constraints. However, in some cases, say the building enclosure is in really great shape, we've got a really great window to wall ratio, not a lot to do, we can really see a reduction in time and cost during design and construction that can get that project up and running and revenue ready much faster for that that owner and development team. Now, in some cases, demo to grade may be, the way to go. And you may say, but demo to grade is not a conversion project. But there are some considerations to take into account if we do demo to grade. So that's kind of what we're going to chat about. So when you're demoing to grade, you do get that flexibility. You can kind of start from scratch when we're going from grade up. But there are additional complexities with our below grade spaces and our neighboring properties that we need to take into account. I really like this slide because it really highlights all of the different performance factors that we look for with the building enclosure. When we're looking at an office to residential conversion, we want to look at, okay, for that office building, how was it originally constructed? How was it intended to originally perform? But now that it's aged, how is it performing now? And that's, what we can find from that condition assessment that we performed. And then looking at towards the residential use, how do we want to transition that performance? What performance requirements do we need that may be a little different? There may be acoustic requirements, thermal requirements, air barrier requirements that we need to consider. And really, how do all of those performance characteristics play with one another? How do they play with other systems in the building, so our mechanical systems, for instance? And then how do they work together for all phases of the building life cycle? Because essentially, we're continuing the building life cycle by converting to a new use. So looking at building enclosure performance, we have our, 4 barriers of the building enclosure. We've got thermal, we've got air, water, vapor, and it's important to understand how all of these play together through that existing enclosure. One thing when we're transitioning to a residential use is that they tend to have higher relative humidity loads, simply because of the uses of the space. I've got bathing activities, we have cooking activities that kind of raise that relative humidity load. And considering we're in a mixed humid environment, we have these interior humidity loads, it's important to really understand how all of this plays with the building enclosure. How is it going to perform? And if any changes that we're making, how does that have an impact? One of the big things that we tend to see too, as we're bringing buildings up to code or changing uses, if we need to increase the thermal requirements to, maintain or to satisfy the energy code. Sometimes we'll say, oh, we'll just slap some insulation on the interior and we're checking the box and we're good. Or I've also had some conversations where maybe we're going for more of a performance-based approach, and we're looking to offset, some of those thermal requirements with some system offsets, and sometimes I've seen it where the insulation has gone tiny, 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 and we have to say, wait, time out. How is this actually going to affect the performance of the building enclosure? And so as we're thinking about this, as we're thinking about use conversions, and we're thinking about making changes to the building enclosure, it's important to note we're not just checking the box to meet the energy code, we actually need to understand how it's going to perform with any of those changes we're making. Another example with that is that, with adding that insulation, how is that changing our dew point line? How is it changing our freeze point line? Are we increasing our, spall risk, for instance, if we have brick masonry or stone through freeze-thaw cycles? And so those are kind of all things to consider as we're transitioning our use type for the building. Now, structural capacity and loading changes. Residential uses also have increased loading. So say we want to have, I want to put a pool on the roof, or say we want to have a vegetative roof for, stormwater capture, or, just for experiential purposes. Maybe we're adding a balcony, changing windows, changing cladding, or even just the, plethora of differences of what's going inside the building with appliances and really what goes into those spaces that's adding on to that existing foundation. And so all of that needs to be considered in close collaboration with the structural engineer. Now, the project we have up here as an example, this is for the former Mazza Gallery project or property. And, okay, you'll say, you got me. It's not an office, it's retail to residential, but go with me here because it's an interesting point, is that this this property is directly adjacent to the metro. And so it was a demo to grade situation. And so they had to be pretty cognizant of those below grade foundations. And so anything that we added back from a structural perspective needed to be carefully considered. And so as you can see there's a concrete plinth on the first levels, and then there's also structural cold form steel to create a little mezzanine level for that concrete plinth. But everything above that is stick-built wood framed construction, which, granted there are some steel tie downs to account for, some other structural components or for like earthquake considerations. But that transition to wood frame construction had a significant impact and a significant reduction if they went with, kind of standard steel or concrete above. Another consideration for the facade, so you see that we have this brick masonry undulating facade. So for this, the lower levels were conventional brick, and then in order to reduce loading, it transitioned to a thin brick element. And it's interesting with that because there are some considerations. One, how with that thin brick, we want it to have this sort of seamless aesthetic for what else is going up the facade. We don't want to point out, hey, that's thin brick versus conventional. There are considerations with how that cladding is being structurally supported off of the backup wall so that it's in alignment, and then how it's interfacing between the two systems. We want to make sure that our air and weather barrier is continuous between the two systems, our thermal barrier, and of course our drainage plane and flashing alignments. And so this is just sort of an example of a couple of design considerations that went into effect when we're looking at loading changes that may happen as you're moving towards a residential use from retail use in this case, but could be an office use. For our below grade spaces, most of the buildings when we're looking at office to residential conversions, there are going to be below grade spaces for either parking or maybe they're occupied spaces. And in many cases, probably most cases, those waterproofing systems are undocumented. They may have been failing, they may be failing just because of the age of the waterproofing system, or frankly, they may just be non-existent. And so as part of that initial condition assessment, it's helpful to understand where are those areas of failure where we may be seeing some water infiltration, and what do we need to do from a repair perspective on the interior side to fix those issues. Now, if we're in a demo to grade situation, we also want to make sure that we are looking towards and designing a continuous we'll make sure that we're designing a continuous and robust interface between the above grade and the below grade, whether that's our opaque walls, so air and weather barrier to that existing below grade, or maybe we're tying into storefront assemblies or to a door assembly. And we like to recommend detailing that robust interface within the design documents, because we may not know what it is today, but at least we're scoping it. So when it's bid out, it's scoped. And then once we get into the CA process, we say, hey, we've got this is the waterproofing assembly that we have. We can then further refine what that detailing looks like. But at least we have that included and have thought through that this is what needs to take place. Another transition to consider are our good neighbor considerations. So as I mentioned, we may be touching a neighboring property on 1, 2, 3 sides, and making sure that we understand what requirements are in place for our neighbor notifications and protections. Are there temporary weatherproofing or sequencing matters that we need to take care of? Looking at the continuity of air, water, and thermal layers. How can we think about that during the design phase before we get to construction and realize, oh, this is something that we need to think about now? And expansion joint considerations too, because many times those can be afterthoughts. And when we have existing buildings and we're looking at expansion joints, those expansion joint conditions can be irregular and in size and substrate and all of the above. And so there are things that's something that's helpful to consider early on and make sure that's also scoped. So I'm going to take you through 2 case studies for neighboring wall interfaces. And I use the term party wall a little loosely here because these are more zero lot line walls versus party walls. But For this particular case, the building was demoed. You could see that, you could see the line of the building that was demoed. The building that was adjacent to it was constructed much more recently. And when the building was demoed, you can see kind of that bleed out of that mortar on the backside of that CMU wall. And that's pretty much because when the CMU wall was built up on that lot line, they can't really get to the other side to clean it up because your building was there. Older buildings, you can see older buildings when this happens, sometimes it can be pretty scary what you may find. So there may be some additional zhuzhing that needs to happen. But for these cases, for this particular case, what we needed to think through with this interface detailing is how can we temporarily protect this neighboring building while construction is taking place. And so we needed to think through what are the appropriate substrates for materials, what substrate preparation is needed because of all of that bleed out, or if there are any voids, what do we need to do to repair that ahead of time? And then also thinking through UV stability. So in this case, we had recommended a fluid applied air and weather barrier that had a UV stability for 12 months so that it could be stable while the building was constructed. You'll also see that, on this side, wait, am I doing it? Nope. Oh gosh, where am I going? Hold on, back. Yes, so you'll also see to kind of the right of the building profile, we've infilled some windows there too. The residential building that was going back was going to be a little bit wider, a little bit taller, and so some of these windows needed to be infilled. So we also needed to look at how are we going to temporarily infill those from an air, weather, thermal perspective, but then also for the long term. And the way that this type of interface detailing and thinking through these party wall conditions is successful is if we think about it through the design process, we incorporate discussions with the architect, with the contractor, with the owner, and also, of course, our neighbor to make sure we're all on the same page and meeting the goals that are set for the project, and we're also providing them protections. This second case study project, so this was a project where the structure and the building enclosure was maintained. And at that party wall line or the lot line, they created a void to, kind of thin up those plates so that we're better accommodating spatial layouts for the units. We're also providing access to daylight and also an amenity space on the lower level. Now, this is a little bit of a different use in that this isn't going to be, the existing wall isn't going to be temporarily exposed, it's going to be indefinitely exposed. And it wasn't really intended for that in the first place. And so we had to really think through, okay, how are we going to incorporate an air and weather barrier? How are we going to incorporate our thermal plane? How are we going to incorporate drainage planes and a cladding system? And another thing to consider is that a lot of times the CMU that's installed, slab to slab right up against that lot line, it's not always installed in a way, probably never installed in a way to anticipate structural loading from a cladding system. And so you also have to think through how is that cladding system going to be anchored back to proper structure so that we can properly set it up on the wall and it's not going to fall down. So you could see on the far side too how the cladding is going up, and so from an aesthetic perspective and also from a performance perspective, we're meeting the project goals of how we're interfacing with that neighboring building condition. So in summary, we chatted. I know this was really quick. We've got 20 minutes, but in summary, we kind of talked through performing those early feasibility assessments to determine, hey, is this project a go, no go? That includes establishing repair, restoration, and replacement decisions and considering design opportunities via those comprehensive condition assessments. Consider, is it better to maintain that existing structure or maybe demo to grade for whatever we need to do to meet those project goals or performance requirements. And as we're converting to that residential use, if there are any changes to an existing building enclosure, how is that being impacted from a thermal and hygrothermal perspective? How are we looking at our tie-ins for air, water, and thermal continuity, especially as it pertains to existing to new tie-ins? And then how can we understand what those project impacts are to our neighboring buildings? So with that, thank you all so much. Those are some little nuggets from some of our recent projects that we've had. So I really appreciate the time, and feel free to reach out if you have any questions or want to continue the conversation. Thank you.
Next up, we've got Peter Schmitt. He's head of technical North America for Siderise. He's going to be talking about curtain wall and perimeter containment, perimeter containment for building enclosures. Good luck with the pointer.
Thank you. Thank you very much. Hello, everyone. My name is Peter Schmitt, head of technical for Siderise North America, and I'm going to run you through some of the fundamentals of curtain wall and perimeter fire containment for the building envelope. So jumping straight into it, there are two primary paths for vertical fire propagation that must be taken into account when designing curtain wall systems, and also the the perimeter fire containment systems that are going to be installed against them. The first is internal, where fire spreads from floor to floor through a gap between the slab edge and the curtain wall assembly. Fire breaks out, combustion products build up, and pressure builds, resulting in fire, smoke, superheated gases following airflow and spreading fire. The second path is referred to as the leapfrog effect, and that is where a fully developed fire at flashover point shatters the lower glazing panel, escapes that space, and then breaks back into the space above. Leaving either of these spaces unprotected can result in fire spreading uncontrollably up the face of the building. Even with a properly fire-stopped void at the edge of slab, the leapfrog effect by itself can cause very rapid fire spread. You can see in this demonstration that despite a properly fire-stopped joint at the slab edge containing flames to that point of origin, after breaking out through the facade, flames are still able to breach the floor above. So this is why incorporation of a protected spandrel panel is so important in curtain wall design. So let's repeat this exercise with a protected spandrel and edge of slab void. The fire occurs in this compartment and is initially restricted to the point of origin, unable to breach through to the floor above due to effective fire stopping at the slab edge. If or when fire breaches that facade, the protected spandrel panel is going to limit the severity of the fire exposure to the facade and vision panel above, buying valuable time before flames are able to spread into that level. Now remember that the objective of passive fire protection, Remember the objective of passive fire protection is not to extinguish a fire, but rather to restrict it to the point of origin or delay the rate at which it's able to spread to adjacent spaces. This is going to afford occupants time to escape to safety. It's going to afford first responders time to arrive on scene and to address the situation. So if we can limit flame spread to this for 2 hours or 3 hours, that's a success. Now this all sounds good in theory, but how do we actually go about quantifying the capabilities of such a system? To do so, the ASTM E2307 testing standard was developed. This standard calls for use of the intermediate scale multi-story test apparatus, or ISMA, which you can see in that detail. The ISMA consists of a test room on the bottom with an interior burner. There's going to be an observation room up top, and those are going to be separated by a floor slab. The curtain wall assembly is going to be mounted to the face of the ISMA, and it's going to feature an opening in the bottom, a window opening, to simulate a broken out window. The perimeter fire containment system, seen circled in the diagram, is going to be installed between the slab edge and the curtain wall assembly. And there's going to be an exterior burner, which is going to be lit at the 5-minute mark to simulate those flames attacking the exterior facade. At the end of the test, the system will have achieved an F rating, expressed as the duration of time it was able to restrict passage of flames to the unexposed side, and also a T rating, which is expressed as the duration of time it was able to limit temperature rise within established limits. Here you can see what the exterior of such a test configuration might look like. In this case, it's a stick-built aluminum curtain wall, a fairly robust spandrel panel there but below the vision glass, and like I said, that window opening through which you can see the lower test chamber and the interior burner. This is what the test might look like at some point after the 5-minute mark, once the exterior burner is lit. And this is what the exterior of this particular test assembly looked like post-test. A lot of people think of metallic components and structural components as being permanent, but in this case you can see that several of those aluminum mullions have completely melted away. Some are very deformed, but in spite of that, the spandrel panel remained in place, maintaining compression of the materials installed at the slab edge and maintaining compartmentation. You can also see some severe discoloration up the face of the assembly. In this particular case, the vision glass did not break, but when testing more critical configurations with shorter spandrels or lower sill heights, it's not uncommon for that vision glass to shatter. So it may have seemed that we had all of our bases covered, but there's yet another path through which flames can race up the side of a building, and that is through the void behind rain screens and exterior cladding systems. Some of you may be familiar with the term chimney effect, which is aptly named for the pressure system that's created when one lights a fire in a fireplace. Flames generate heat, cause that heat, and then smoke, hot air, wants to rise up that chimney, but to do so, something must take its place underneath. So that creates a negative pressure system, drawing oxygen-rich air in through the bottom and pulling flame, smoke, superheated gases up that void. Now this is very clearly shown in this demonstration, where despite not having any combustible materials within this quote-unquote chimney, you can see that the small fire at the bottom is drawn up several feet simply by introducing that tube. Here I have a couple unfortunate examples for you of where the chimney effect came into play. On the left, you'll see Polat Tower in Istanbul, where despite having effective vertical compartmentation which restricted flame spread across the building, the horizontal fire blocking was not properly implemented, resulting in flames rising very quickly up 42 floors to the very top of the building. On the right is another example, this time out of China, where you can see that, and I'm unable to pan through this video. After about a minute or so, the flames were able to spread 6 to 8 floors. Another 30 seconds or so beyond that, and the flames had risen all the way to the very top of the building. Another 2 minutes or so after that, flames had completely engulfed the side of the building, and flaming material was shedding down and falling to the ground. I'm not going to make you sit through this whole video, though. So how do we go about effectively protecting these voids? Well, a lot of rain screen and cladding systems are designed to permit ventilation upward and drainage downward during normal operation. So installation of a continuous full-field barrier, such as the one shown on the right, would not permit proper functionality during normal operation. One solution is to utilize horizontal open-state fire blocking. And such barriers are generally comprised of a highly fire-resistant insulation material, such as stone wool, with an intumescent material positioned on the outermost face. That intumescent is going to be offset from the exterior cladding such that it is able to permit ventilation upward and drainage downward under normal conditions, but in the event of a fire, the intumescent will very rapidly expand to close down that air gap with a dense char and restrict the passage of flames and smoke upward, maintaining compartmentation and eliminating the chimney effect. Now, once again, this sounds great in theory, but how do we go about ensuring that these open state barriers can perform as needed? Well, years ago, the ASFP developed a technical guidance document, TGD-19, to provide a means of evaluating the capability of such barriers to close down the gap and continue to maintain compartmentation. This has since been further refined into the EN 1364-6 standard, which was published within the past year or so. Now, I won't go into too much detail on this test method, but you can see there that the barrier will be installed between 2 concrete lintels with corresponding cavity insulation above and below. That will be mounted on top of a test furnace. There will be a 5-minute window during which flames and heat are able to bypass the system, but by that point, it must have demonstrated the capability to close down that air gap, and then it must restrict the passage of flames and heat for the rest of that duration. Now, this demonstrates the ability of the barriers themselves to provide the necessary performance, but how might we go about evaluating the performance of the full exterior wall system? One full system testing standard, which Daniel actually commented on earlier, is NFPA 285. You can see from the diagrams that the arrangement is reminiscent of ASTM E2307, but there are certainly some notable differences. It has two chambers, that test chamber on the bottom and another test chamber up top, a second story test chamber. There's an exterior burner, and once again, there's a window opening towards the bottom. Now, one notable difference is that the interior and exterior burners are going to be lit simultaneously at the beginning of the test. And that's because this is intended to simulate a post-flashover fire already venting out of the window. Now, of course, we don't want to see flames breach the second story test chamber, but performance at the slab edge, unlike ASTM E2307, really isn't the focus here. Here we're trying to evaluate how readily flames and heat are able to spread over the exterior surface and also through that cavity. As Daniel alluded to earlier, failure will be observed if the flames exceed 10 feet vertically or 5 feet horizontally, or if the temperature exceeds established limitations. So here you can see two drastically different outcomes of similar NFPA 285 tests for the same terracotta panel system. The one on the left was conducted without any fire blocking and very clearly didn't go so well. Upon review for the retest, the cladding manufacturer opted to A, utilize a less critical insulation type, and B, utilize fire blocking within that cavity, horizontally at both levels and vertically on either side of that window opening. You can very clearly see the difference that made, those two modifications, to significantly restrict the spread of fire within that cavity. So we know that certain fire stopping and fire blocking methods can be very effective at restricting the spread of fire at the building envelope, both internally and externally. But it's important to keep in mind that the performance of such systems can only be as good as the quality of the installation. After spending well over a decade in the passive fire protection industry, I've seen some truly nightmarish installation photos that almost make these look compliant. Everything from tin cans to cotton shirts shoved in the void. And the challenge is that sometimes these systems are not inspected until after certain things are already concealed. So beneath sprays, beneath flashings and whatnot, it makes it very challenging to verify that everything's been properly inspected without doing destructive testing. So this is why it's very important for fire protection manufacturers to properly educate and support stakeholders throughout the process and provide them with the necessary services and tools to ensure a quality installation. What does that mean? It means technical support during the design and specification phase. That means product training for designers, specifiers, etc. It means on-site trainings and mock-up installations to demonstrate what compliance looks like. And it means, of course, inspection to flag nonconformances at various phases before it becomes a bigger issue. Free inspection services offered by passive fire protection manufacturers can quickly identify areas in need of remedial actions before the works progress further, helping to save time and money while ensuring a consistently compliant installation across the project. Many manufacturers also offer apps which can provide a comprehensive, clear report to log and verify the installation quality throughout that process as well. Now, these tools and services are fantastic to help save time and money, to avoid problems down the road, but ultimately, we want to make sure that life safety is not compromised at any point in this process, and this helps us do so. Thank you very much, guys. Feel free to swing by our table to discuss further, or reach out to me directly. I'd be happy to speak with you. Thank you.
Just a couple notes before I introduce our final panel. Just a reminder that all the speakers for this session should come back up to the stage at the end of the next panel to take photos. And a reminder that the AIA sign-in sheets are at the registration desk. And also just a reminder, if you wanted to stick around for some post-event refreshments and schmoozing, they'll be there. So our final panel, I'll introduce our moderator, Rens Gill. He's a principal with Beyer Blinder Bell. And that panel, and he'll introduce the panel when they come up. And they'll be talking about the intersection of historic preservation and modernization.
So another panel discussion, what we thought we would do is go through a few projects, 3 to be exact, give kind of an overview, and then do a little Q&A back and forth to each other, but that way you have a little more bearing on what the projects are. But I'm Renskill from Beyer Blender Bell Architects. I'm a principal there.
Morgan Reynolds, Associate Principal at Thornton Tomasetti, Facades.
I'm Amanda Edwards. I'm a principal with MTFA Design and Preservation.
And Johan Morthorst, Principal with Kieran Timberlake.
All right, we ready? Okay, so I'm going to start us off. And let me just make sure I get this working okay. So today, the first part of our panel is going to discuss the Folger Shakespeare Library. And this is really a project in 2 parts. So the first is the exterior envelope restoration, which was done by MTFA. And the second is the museum edition that was done by Kieran Timberlake. So the building was designed in 1932 by Paul Philippe Cray for Henry and Emily Folger to house their, at this point, 79 first folios of Shakespeare's work. But they really wanted it to serve not only as a place to house their library, but also as a cultural institution for the city. To the Folgers, the wisdom of literature and history were indispensable to the life of a democracy. So putting this right at that civic core was important. So located at the edge of the civic core on Capitol Hill, it's near the Supreme Court, the Library of Congress, and the U.S. Capitol. The building really bridges this public architecture with a 19th century neighborhood of row homes, and it bridges it through its scale, its artistry, and its purpose. Cray designed the building in what's called a stripped classical style with Georgia white marble by the Georgia Marble Company. The marble was touted as 98% pure calcium carbonate, had a strength of 10,000 psi, and an absorption rate of 0.005%. So this was the best marble they could find. I want you to notice the fluted columns, the alternating ashlar courses, the scalloped parapet, and really the artistry of the bas-reliefs on that north facade. This classicism contrasts with the elaborate Elizabethan interiors that transport you to Renaissance England. So from 1932 to 2018, the building's appearance was severely altered by a corroding, lead-coated copper flashing, and I'm going to try this, let's see. Up at the top, right here, I did it. So as the lead was wearing away over, several decades, the copper was exposed, and it imparted this deep black stain around the entire perimeter of the building. So the library's priorities were to address this stain, to address inappropriate sealant joints that were on a solid masonry construction, and to address marble spalls at the shelf angles that were found on every elevation. So the first step was addressing the stain. This is where I come in. I'm an architectural conservator, so my expertise really is in how to restore these historic materials. So through careful testing, we identified the stain as copper, and it had penetrated the stone to a depth of about 1.5 millimeters. The treatment required a very specific sequence to remove that stain. The first, we misted the stone for 3 hours. That opened up the pore structure of the stone. We followed that as it was still wet with microabrasives, that's 30 psi of an inert soda glass. And then we applied 2 applications of a clay poultice using ammonia-based copper remover. And I tried each of those things in all the permutations, but it was only in that actual sequence that it was able to remove the stain. And you'll see in photograph D, that little tiny square gave me the hope that I could do this around the entire perimeter of the building. And then in picture E, we looked at it under the microscope to make sure that we were really fully removing the stain. And so that's the before and after. So how did we do this? This is a sign when we were an existing condition on the left, showing how deep that stain and how black it was. We applied the poultice with a sprayer. We put a very thin layer of poly on it in order to prevent it from drying out too fast. And we did that twice. We were able to bring it back to that original bright white Georgia marble in its intended appearance, which is pretty incredible. Here is a in progress photo. We did this in phases around the building, and yes, I was very worried about that transition, but the good news is that you can't see it. So we worked around the building to remove this stain. We replaced that lead-coated copper flashing with a marble cant so that it was still shedding water, but it's not visible from the ground. So while we were focusing on the cleaning, we were also looking at how to repair the marble. So there were these falls occurring, and you can see some previous repairs at the steel shelf angles. So in the 1980s, this building had been repointed with sealant. So for a solid masonry construction, you know that's just trapping the moisture into the building wall, and all of that moisture was sitting on top of these shelf angles, allowing them to corrode over time. So we had to find all the steel. So we had original drawings, but of course the shelf angles were not in all the same places that the drawings showed. We did some GPR, we located that, and then we had to open it up to see what its condition was, to see what needed to be replaced, what could be treated in situ. And so we did a lot of work that you wouldn't be able to tell because of the precision of the masons we were working with. So the remedy, let me get this here. So we replaced the severely corroding shelf angles with stainless steel. We removed those ashlars and put them back in their correct locations with stainless steel pins. And then we repaired the damaged marble with stone Dutchman. And then we repointed all of the joints with a compatible mortar to get that water vapor transition happening correctly. So the question, this is the end result, which we think came out pretty great, very close to that 1932 appearance. And so why did they do all this work before they decided to do a major underground renovation addition? First was really to stabilize the building so that all of that interior work could happen. And then next, I think it was also to show that they were good stewards of this building, to get some good fundraising going, because look how beautiful this building is, but also to build that trust that as they took the next step, they would continue to serve the library as best they could. And I'm going to pass this over to Johan, who's going to tell us about the next part.
Yeah, so Kieran Timberlake was engaged initially as for a master planning effort that led to a kind of comprehensive renovation and addition. And the context for that was that since 1930, when the original Cray building was completed, the mission of the Folger as an institution had evolved pretty significantly from a fairly exclusive, research-focused entity to a much more outreach-driven mission that was really focused on trying to bring Shakespeare to as wide, broad, and diverse an audience as possible. And so in many ways, the Cray design, as beautiful as it was, became a bit of an obstacle for that expanded mission. It read as not necessarily welcoming and perhaps even not even open to the public. It had a host of accessibility issues that you can see some of just in the number of stairs just to get into the building, and then more so once you're inside. And it just lacked the kind of spaces for the exhibition and educational programming that had become part of what Folger did today. So our charge really was, in some senses, to make an entirely new front door to the building and do so without altering the historic facade or massing towards East Capitol Street. And we did that by inserting a new addition with visitor amenity spaces and exhibition spaces below the existing historic terrace, and allowing one to enter those through these generous, gradually sloped gardens that really are intended to greet the visitor at the sidewalk and bring them into the building. Those entry gardens become the beginning of what we understood or conceived as a kind of continuous topography that goes from 2nd Street into this new addition and then back out to 3rd Street on the other side. So that the entrances were fully accessible through these gradually sloped walks, but so too were other existing portions of the surrounding landscape and that historic terrace with its fantastic bas-relief sculptures on the East Capitol facing facade. And then once inside the building, the addition provided much needed exhibition and educational programming, as well as visitor amenity spaces, expanded box office, restrooms, gift shop, and the like. And at the center of that is this North Shakespeare Exhibition Hall. And at the center of that is that, one-of-a-kind collection of 82 copies of the first folio, the largest of its kind in the world still today, which were out on display now for the first time in the Folgers' history. So that new addition, as I said, was kind of inserted underneath the historic terrace, and then existing former stack spaces, storage, and staff workspaces within the existing basements were also converted to additional exhibition space, and all the floors in there were lowered. So the primary structure of the building is a steel-framed building, and those new floor levels basically had to come in below the existing footing level of that steel structural frame. So in order to do that without the space impacts of conventional underpinning, we worked really closely with our structural engineer, who was Silman, now T.Y. Lin, to devise a kind of strategy of inserting new columns between the existing with lower footings, transferring those loads over, and then cutting out the existing columns. And then in some cases, in a few select instances, extending the existing columns down with new piers and footings down to levels below the new floor level. The other complication to all of this was that the facade that Amanda just described, the restoration of that primary north-facing facade, was self-supporting down to the basement foundation wall. It wasn't hung off of the existing steel structural frame. So that existing basement foundation wall was to be entirely removed, so we had to temporarily support that facade through the course of construction until the new addition was kind of complete, structurally complete, and could rest the new facade on that addition. So what you see here during construction, the large tube steel across the front, the kind of needling plates, the posts that are supporting the tube, and those kickers back, that's all the temporary steel supporting the facade during construction until that addition is built.
Now you can see why we wanted to make sure the facade was stable.
The other thing you can see just to the left of the first of the foam kind of protective panels that are protecting the bas-relief panels is a little black piece, which is one of several motion and vibration monitors that were installed to track movement during key construction activities and throughout demolition and construction to make sure that we weren't introducing any risk of cracking or damage to the existing facade. And so you can see that temporary support again on the left, and on the right you can see the beginning of the demolition activities after that support has been put in place, removing that basement foundation wall. The primary structural transfer as well, on the left is an example of a new pier being installed underneath the existing column that's temporarily supported. And then on the right slide, you can see an instance of one of these new columns that's been introduced between the existing, and just beyond it, one of the existing columns that's was subsequently cut away after that transfer was implemented. And so in order to do those structural transfers without, again, introducing risk of damage to the facade through settlement or deflection, the variety of sort of hydraulic jacks were used to both take settlement out of the new footings, kind of preloading the soil against the weight of the building, and also to take deflection out of that transfer girder before the loads were shifted over. And in the center bottom there, you can see an example of one of these pancake jacks that were used to load the piers against the underside of the existing column base plates, and then once fully loaded were grouted solid and then the shim space packed out. And so the tie-in between the waterproofing over top of the new addition and the existing building was kind of a critical detail that actually evolved quite a bit during construction once we got into it. The original plan, which you can see on the left, was to actually remove the entire water table base course of the stone facade in order to provide access to that condition, rebuild the backup wall, and then tie in the hot mopped, fluid applied waterproofing system that was over top of the addition up that backup wall and lap it underneath a self-adhered sheet membrane system in there. When the contractor got involved and the trades got involved, they advocated strongly for not removing that base course, for leaving that in place for a variety of reasons. Just the scale of those pieces of stone and the difficulty in removing them, the risk of damage to the stone, the additional complication that would have been introduced to the temporary support that we just saw. And those base course stones also supported those highly decorative bas-relief panels that were really one of a kind and could not be replaced if they were to be damaged. Leaving that course in place introduced a lot of complexity to this detail, though, both in terms of not being able to get access to that backup condition to rebuild it easily from the outside and do those tie-ins, and also then in terms of the kind of safety considerations that the trades brought to the conversation in working with the hot mopped material in a pretty confined space under there. So what we ended up doing is working closely with them, working with SGH, who was our envelope and waterproofing consultant. We kind of reconceived this detail in such a way that the backup could be built from the inside as a kind of two-tier shaft wall construction, which allowed us to introduce some stainless steel flashing over top of the first stage of that, and then tie in or transition between the hot mop system on the roof of the addition and the stainless with a PMMA cold applied system in there. Then the closure could be completed on top of that stub wall with a proper air barrier in the inside layer, all of which was done from the inside. And this is kind of that condition during construction. You can see in white that transfer girder. You can see the dead ends of the PT slab before the concrete's been poured, and all the steel at the top is that temporary support for the stone above, which you can just kind of see sitting on those needle plates. So working through this during construction, we, as the architects, were working quite diligently through the digital model that you see on the right to really try and track through all of those transition conditions in 3 dimensions. But then the contractor was also working on site with the trades, and they built this plywood mock-up as a way of validating the working clearances and had the trades all interact with that directly and kind of sign off on, yes, we can do this, so that once we committed to this detail, we weren't going back on it. And you can see some of those detail conditions during construction here, particularly on the left, that PMMA transitioning up over the stainless steel flashing, which is capping that little stub piece of wall, which then gets closed up above it afterwards. And then all of that is essentially invisible in the end result. The only trace of it really is this blackened steel fascia that you see in the foreground here, which sits right in front of that transfer girder, directly beneath the exterior wall of the existing building. So everything beyond that is the new addition, and everything behind that is former basement space of the existing Folger. And in the foreground there, that wood-clad box, that's the new Shakespeare gallery with those first folios in the middle of it.
So I think that kind of explains why it needed a bigger overview than just launching into questions. But one, I was going to ask, because it seemed like you were working through some of the details during construction. Did you have a contractor on for pre-con, or is some of this just sight unseen? So how did that work?
Yeah, it was a mix. So we did have a CM on board for pre-construction services, and they did engage some trades in early involvement. But a lot of the focus at that stage was on the mechanical system coordination and the complexity of that. This was a building that, when it was initially built, had a coal-fired boiler in the basement that generated steam for steam radiators. At some point was transitioned to Architect of the Capitol central plant chilled water and steam, and had accumulated sort of a collection of air handlers, steam to hot water converters in what I think were 18 discrete mechanical rooms sort of stitched in throughout the building. So that's principally what we were focused on during pre-con, and frankly, the complexity of what was going to be involved with that temporary support probably didn't bubble to the surface because there was only so much bandwidth. But the other half of that was a lot of the not assumptions, but a lot of the visibility that we had to those hidden conditions from the existing CRAE drawings were pretty limited, right? I mean, those drawings did a beautiful job of representing a kind of representative condition, a typical condition, and they left a lot to the builder and the architect to kind of work out in the field in the day. And what actually happens along that face of that wall, I think there were probably 10 or 12 different conditions in terms of the relationship of the steel to the backup wall to the marble and whatnot. So a lot of that just kind of had to be worked out once we really got into it and opened it up.
I know it also kind of the project happened in 2 phases. Did you find advantages, disadvantages of it kind of being somewhat separated, or you found more information before you got to start?
Yeah, I mean, I think, like I said, being able to think clearly about how the building was put together, we were able to help some of the conversations that you guys were having. But I think the biggest issue was making sure that all those joints were tight, and so that when everything was opened up, we knew that that those stones were in good condition and that we weren't going to be worrying about things falling off the building.
Yeah, I think it was also, as Amanda said briefly in her presentation, it demonstrated, I think, to the broader public and the community and to the historic preservation kind of reviewing authorities, the Folgers' commitment to be good stewards of the building, right? I mean, it gave them credibility in that role. I mean, they had always been stewards of the building, but this is it's a nationally National Register listed building. It's one that the surrounding neighborhood has a lot of possessiveness around, right? It's a real community amenity. And I think that gave them a lot of goodwill and proof of intent as well. It also, frankly, just generated some excitement about what the building could be, and probably supported their fundraising efforts for the larger project as well.
I was just going to ask, because any restoration project requires a fair bit of artisanal labor, and especially when you're working at a scale of the entire building envelope, what was the process for benchmarking with the laborers, and they're working across multiple crews, making sure there's a clear understanding of this is the goal, this is the process? If you could talk about that.
Well, from my point of view, it was actually a very small crew, maybe 3 or 4 people that were doing this work as they were phasing around the building. So the mock-up process became very important, making sure that sequence was well understood and how do we move around the building. And then, just being present often to check the progress of the work was very important. So overall, it was very smooth. And we are lucky that in DC, we have a number of really good restoration masonry contractors. And so it is a good partnership when we're working in the field. We're learning from each other, but there's a lot of trust as we go through the process.
I think maybe the last one I was going to ask is, with that neighborhood having real ownership of the project and what it looks like, what was that review approvals process? If you changed something in construction because it was unforeseen, how did that work out?
Yeah, I mean, I think anybody who's worked in DC, either in or adjacent to the Shipstead Loose district, kind of knows how complicated and lengthy that kind of permitting process is, and how open it is to public comment and opinion. In this particular case, we worked really closely with the DC Historic Preservation Officer and the Historic Preservation Review Board prior to the kind of public hearings, as well as with the U.S. Commission of Fine Arts, who had oversight over the project because of its location, and their staff. But then the other overlay is that, again, if you're familiar with DC, unlike Philadelphia, where we're located, or a lot of other kind of major East Coast cities, the property line on these lots often sits not right behind the sidewalk, but quite a ways in. And there's this zone that's referred to as the parking, which is maintained by the property owner, but part of the public space. And a significant amount of the project of the renovation, the entry gardens, and frankly, the addition and the terrace sits outside of the property line. It's in public space. So it falls under review of the Public Space Committee, as it's called, and they're really looking at it through the lens of, if we're allowing you to do these modifications in the public way, what benefit do they offer to the general public? And so a lot of the landscape design, the development of those entry gardens really was developed through the lens of those spaces and that environment being an amenity to the broader public, a space that people could recreate in and sit and use, irrespective of whether they have any intention of entering the Folger or using the or accessing the Folger facilities. So that was a big part of it.
I think we may move on to the next one. So the next one we're going to talk about, and you'll kind of see a theme here of adding to existing buildings, but also creating kind of, in some cases, primary or secondary dignified entrances to buildings. So the second one is the National Museum of American Diplomacy. So this is at the Harry S. Truman Building, which is currently Department of State, originally designed as Department of War. So this will be helpful for later to what we were trying to get back to, but this is it when it was completed in 1941. Kind of a close-up of that. Some of the sculptures were never actually implemented. These are just mock-ups. Then, of course, as time goes on, in the 80s, they added kind of these canopies off the front of the building, and then in the 90s added a security pavilion under them. So it's not the most dignified entrance at that point. So we designed a new entry pavilion and museum that goes at the forefront of the building. So kind of one of the goals was not to be the first thing you see as you walk in is security. So it's kind of tucked around the corners as you enter. And so one direction is for staff, the other is for guests, with then exhibits in the center. And one of the main goals was how do we kind of tie the buildings together without putting something structural right in front of the existing building. So we looked at tying into the existing historic columns. And so, of course, this being a federal building and very prominent, was also reviewed by CFA. This detail kind of shows how we're tying it together. And one of their main concerns was to limit how big that lid got that was sitting on the kind of the plinth. And I think somebody mistakenly said in the meeting that it would only be 24 inches. So it forever could only be 24 inches, which was then Thornton Tomasetti's problem. And then here is kind of in construction, the doors are behind kind of the scaffolding, and you can see where it's starting to tie into those beams, but kind of keeping all the structure out and away from it, to ultimately land in an end condition where it kind of still has that same feeling of the historic entry, very dignified, restoring kind of the doors, and you'll notice some of the panels are slightly different, which is where the 1980s canopies tied into the building. They weren't as thoughtful back then of keeping things separated. And then we're going to do another one and then kind of toss questions between the two of them.
Choose the one,
the big one.
That one will hold the two on that.
Yeah.
So the screen, like if you hold down that, they'll. Okay. So it's a little bit of a different animal, let's say same species. This is the Washington Monument Visitor Screening Facility. So I've talked about preservation projects where we're actually like lifting up buildings, adding to them. This was a little bit of a different one where we were engaged to create a replacement for what was a temporary screening facility. But the partie was that it could not actually anchor to the monument. They didn't want to create any load imposed onto the monument. And the idea is also had to be somewhat demountable. There's this logic that when you add to an existing historic building, especially from a security perspective, there's a point in time when world peace will be declared and we will no longer need these secure checkpoints. So that was one of the ideas, is that this would have to be ultimately taken apart if and when the time comes, which is not looking likely. So a little bit of history. So the monument was constructed in 1884. And then its first major upgrade was to change from a steam-powered elevator to an electric elevator. And this allowed people to get up to the top really quickly, but it also increased the demand when it came to amount of visitors, the volume of people coming to visit the monument. And the strategy before 9/11 was people would just queue outside and mill around until it was their turn to go up. Obviously, after 9/11, different landscape. And so what was built was this very severe example of form follows function, concrete bunker, reinforced masonry block with very, very small windows. And this was the kind of temporary solution to how do we control flow and visitors. Now, anybody who's visited, I imagine everyone in this room has probably been to this building. The average flow is about 2,000 visitors a day. So this was not really servicing their needs. It was very congested, very narrow, not a pleasant experience, not a dignified entrance, but it met the requirements from a security perspective. The other thing to look at here is the size of the windows, right? We were kind of tasked with meeting structural performance, envelope performance, but also protective design. And conventional security glazing looks like that, and this was not the idea. The present day solution we came up with was with BBB was a highly transparent glass box. As you can see, there's kind of a rejection of what was there before. So celebrating transparency, glass was a clear, distinct choice to kind of reject that idea of a bunker. It presented its own challenges from a structural perspective, from a mechanical conditioning perspective. But the idea here is also we wanted a distinct identity for the pavilion from the monument. So it's clearly not a historic material, glass and steel frame construction. The other idea of that is you want to celebrate but have its own identity. So the massing, the pure cubic volume, the reinforcing of the rectilinear grid there is a way of kind of connecting back to this neoclassical motif of the Washington Monument. One of the other challenges was there was a lot of iterations in the design schemes to get to this point, and there's a lot of changing of goalposts in terms of the performance requirements. So once the design was selected, then the performance criteria were established. But ultimately, this was the intent, and the idea of celebrating not only transparency, but there also was a need for privacy, a need to maintain security. This is a very public site. There's, like I said, a large volume of visitors every day. And so trying to balance these needs of limited footprint with getting to work structurally, to work from a performance perspective, from a protective design perspective. So the idea here was to try and push all the structure to the outside. So marry the facade, marry the protective design, and marry the structure into a single integrated system, a building skin. So steel frame construction, no interior support columns or anything. The way that the security was handled, requirements were handled, was very much through the way the flow was designed. So you come in along the south, and there's this quick dog leg. So you come in, and then you're immediately in the secure zone. There's a glazed partition wall and door, and then as you move forward into that next zone, this is where kind of the forced entry. The forced entry was not on the outside of the building. It was we had the ballistic resistance and the blast resistance to compromise the glazing, but we followed a layered approach where you had the outer line on the east and west elevations. The outer line was the blast resistance and the energy performance resistance, so it's a laminated IG unit, and then on the interior side of the steel is where we had the ballistic resistance. And the idea here was, if anybody's worked with security glazing, it's very heavy, very dark. And so it would have operated at cross purposes to allowing light and transparency into the space. The true point of, let's say, like the hardened line is really when you get to the back, and that's where you have the reinforced concrete access point before you actually get into the monument. The other nice thing here is the 2 points of egress. So once you come out, you get people out quickly. They have the option of going directly out the side, or they can walk back through. Going back to the idea of the structural isolation, so it's a completely separate foundation, divorced from the monument. There was a desire not to impact the existing integrity of the building. And then can't really see it here, we put all the mechanical systems, electrical services below, because you wanted to have this glass box. And then the connections of the steel frame, it's all welded connections, but at the bottom, that's where you have your base plate, and that's a bolted connection. So that going back to the idea of demountability, but also it's balanced design approach where you want to limit the amount of load that gets transferred back down to the point where you have some common linkage between the existing monument and the new pavilion. Getting back into the details of the facade, so left is out, right is in. So this is kind of showing you the cross-section through the facade. On the left, you had the laminate IG unit, where we also integrated a stainless steel mesh, and the idea of having the low-E-coated glass, the mesh kind of on the outside, the blast-resistant portion, and then on the right is the ballistic resistant. So separating the two, it allows for a much lighter or increased amount of visual light transmittance can pass through the building into the interior. The other idea of it does serve a physical security application, in the sense that now on the inside of that steel, all of that facade is blocked by the interior glazed system. So the outside was, it looks like structurally glazed. It's actually captured with a rebated spacer and intermittent toggle fasteners. And then the interior is a more conventional pressure plate beauty cap captured system. The other thing I would say there is security glazing is very heavy. So the idea of separating the two into two separate glazing panels means installation doesn't require heavy duty robots, and also the need for any future maintenance reglazing. You don't have the same challenges because the glass can now be easily picked up and taken off and put back on. Aesthetically, the other real goal here was to eliminate the very dark and opaque appearance of security glazing. And so first idea was, okay, we want visual light transmittance. It's obviously going to be low iron glass. It's going to be a neutral low E coating. But now it's an all glass building, so you're going to have higher demands for mechanical systems if we are allowing loads of light in. So, everyone who works with low E coated glass, there's always balancing the solar heat gain coefficient with the visual light transmittance. Here, the coating favored visual light transmittance at the expense of solar heat gain, and so the mesh helped to mitigate things like solar glare, help mitigate and bring down the solar heat gain coefficient without sacrificing the neutral appearance of the glazing. And then it also allowed for this type of glowing effect at night, so it was very dynamic. So during the day, you had this, this solar shading built into the glazing assembly. At night, because of the backlighting and the ability to light from the interior, it became a glowing object. And I think this is a really good example of how it is a completely distinct design. It is a different material choice, different palette, but it still harkens back to the neoclassical look, and the dynamic quality of the stainless steel mesh with the low E coating and the brushed steel cladding really does blend in at certain times of day with the existing limestone.
So with that, you can see why it's so important to get an engineer that understands aesthetics.
Appreciate it, yeah.
So I guess with either of these, but how do you balance kind of the protective design with structure, and how, I guess, having both in-house capabilities, like how do you see that work? Does it, a team?
Oh, definitely. Integrated services is kind of critical especially when you're dealing with something with such a taut envelope system. The protective design engineer will develop the loading requirements. They'll tell us actually what we need to do, and then that informs the structural design, the amount of hardening needs to be done to the steel frame or the base building structure. It also very much dictates the glazing assemblies. And one of the challenges in dealing with security glazing and protective design applications is the pool of available bidders and the amount of testing and it's very bespoke engineering analysis that goes into being able to justify you're able to meet the performances. Being able to do that work internally before we go out to bid means we're cutting out a lot of the guesswork and potential change orders, because the design has been validated by the design team before it goes out to the contractors.
I guess going to the previous project at the Diplomacy Center, how do you go about analyzing, like, if a structure can take it with a building that old with limited drawings?
Yeah, I mean, the first point is always to start with what you have and not cut holes into the wall. Right? So going and looking at the existing structural drawings will tell you roughly the wall thicknesses. It'll tell you the strength of the concrete, but you ultimately need to then do GPR, radar, and look and scan for rebar, because that's the big variable. It may not be where you think it is.
That's very true.
Yeah. And then on top of that, is the concrete the actual strength that it says it is. So there you're taking core samples of the wall, sending it to a laboratory. They're doing destructive testing of those core samples to determine the compressivity of the concrete. And then ultimately, all of that information gets fed into an analysis model. And so that's where we start to test, okay, and the more tests you do, the more samples you take, the more you can reduce your factor of safety and you can make less conservative assumptions, but all of it gets fed into a structural analysis model.
I think with that, we're at time. So thank you all for your time.
Thank you.
Yes. Thank you.
Just a reminder to the speakers to come up for photos when you get a chance. Thanks.
And
go.
And let's give Martina a big round of applause. She did a fantastic job today. And to all our speakers and sponsors. And thank you all for coming out today. I know it's not that far, a little farther than I thought it was going to be, but welcome. And welcome to the reception. There's a little reception afterwards, so stick around for a bit. Thanks.